On October 26, 2004, Cassini's radar pierced Titan's atmosphere for the first time and captured something that shouldn't exist. A bright radar return, 150 kilometers across, glowing against the dark terrain like a scar. The signal was so strong that atmospheric scientists ran the numbers 3 times, convinced the instrument had malfunctioned. Methane lakes were theoretical. Liquid hydrocarbons pooling on a frozen moon 1.4 billion kilometers from the Sun violated every atmospheric model NASA had built. The brightness meant a smooth surface, mirror flat, reflecting radar back like polished metal. But the chemistry required to keep liquid methane stable at -179 degrees Celsius under 1.5 bars of pressure, with solar radiation constantly breaking it apart, didn't add up. Mission planners had designed Cassini to map Titan's surface, expecting rock and ice. Instead, they were staring at something that looked like Earth's oceans, made of a substance that explodes on contact with our air. The data log from that pass is 47 megabytes of radar returns that rewrote planetary science textbooks. In 2004, no one knew what was waiting beneath those orange clouds. Titan is the only moon in the solar system with a thick atmosphere. At 1.5 bars surface pressure, it's denser than Earth's, wrapped in a photochemical haze so opaque that every telescope, from Galileo to Hubble, saw nothing but an orange sphere. No surface features, no mountains, just unbroken color, 5,150 kilometers wide, hiding everything beneath. That orange comes from tholins, organic molecules formed when solar UV hits nitrogen and methane 600 kilometers up. The particles scatter blue light and let red through, staining the entire moon the color of rust. For 300 years after Christian Huygens discovered Titan in 1655, astronomers assumed it was a dead rock wrapped in poison fog. Then in 1944, Gerard Kuiper pointed a spectrometer at Titan from McDonald Observatory and detected methane absorption lines at 619 nanometers. Methane, not nitrogen, not ammonia, but CH4, a hydrocarbon that on Earth comes from biology or volcanic vents. On a moon colder than Antarctica in winter, with no volcanic activity, methane was as out of place as finding gasoline in your bloodstream. What scientists didn't realize was that methane shouldn't exist in Titan's atmosphere at all. Solar ultraviolet photons break methane molecules apart in about 10 million years. The reaction is irreversible at Titan's temperature. CH4 splits into hydrogen, which escapes to space, and carbon, which rains down as tholins. Run the math, and Titan's atmosphere should have been stripped of methane 400 times over since the solar system formed 4.5 billion years ago. Yet spectrographic measurements showed 5% methane by volume, stable across decades of observation. Something was pumping 300 million kilograms of methane into the atmosphere every year to replace what UV destroyed. The only explanations were active cryovolcanism, venting methane from a subsurface ocean, or surface reservoirs large enough to evaporate and replenish the losses. All three required liquid methane, which required temperatures and pressures no one had confirmed. By the late 1970s, theorists had sketched models of methane rain, rivers, maybe even seas. But models aren't data. Titan's surface remained invisible, the methane source a hypothesis with no evidence, and the replenishment mechanism pure speculation. And in 1980, Voyager 1 would send back the first clue about where that methane was coming from. Voyager 1 screamed past Titan on November 12, 1980, at 6.5 kilometers per second. Its instruments measured surface pressure at 1.5 bar, 50% higher than Earth's sea level. The atmosphere wasn't just thick, it was denser than ours. Nitrogen made up 95% of it, with methane and trace organics filling the rest. The haze that blocked visible light was photochemical smog, hydrocarbons cracked apart by sunlight and reassembled into aerosols. Every image came back the same: a featureless orange disk, no surface features, no contrast. Voyager scientists did the math. With that much atmospheric methane and surface pressure above water's triple point, liquid methane should condense, rain should fall, lakes should form. But the cameras saw nothing, and infrared couldn't penetrate deep enough to confirm. The hypothesis sat in papers for 2 decades, cited but unproven. Titan had the conditions for a methane cycle, precipitation, maybe even standing bodies of liquid on its surface. But proving lakes existed would require a mission designed to pierce the haze, and that mission was already being planned. Cassini-Huygens launched from Cape Canaveral on October 15, 1997. The orbiter carried synthetic aperture radar tuned to see through Titan's atmosphere, plus infrared spectrometers mapping surface composition. The Huygens probe, built by ESA, packed cameras, a gas chromatograph, and landing gear engineered for ambiguity. The lander's designers didn't know what Titan's surface was, so they built it to survive a splashdown into liquid methane or a hard impact onto water ice. The hull could float. The instruments could function wet or dry. Every system had a backup, calibrated for conditions nobody had seen. It took 7 years to reach Saturn. Cassini entered orbit on July 1, 2004, burned 60% of its propellant in a single maneuver, and locked into a trajectory that would loop past Titan 127 times over 13 years. Huygens sat clamped to the orbiter's side, waiting for release. The mission had $3.26 billion riding on instruments that had never been tested in an atmosphere like Titan's. What the engineers didn't know was whether Huygens would splash down into an ocean or crash into ice. Cassini's first radar pass happened on October 26, 2004, 4 months after orbit insertion. The synthetic aperture return came back in strips, each pixel representing 300 meters of Titan's surface. Bright patches scattered the signal hard. Dark patches swallowed it. Radar brightness meant roughness. Bright regions were jagged, textured, chaotic at centimeter scales. Dark regions were smooth, flat, maybe the smoothest natural surfaces the instrument had ever seen. The distribution wasn't random. Dark patches pooled in low-lying areas, exactly where liquids would collect. But radar couldn't distinguish between solid and liquid if both were smooth. A frozen methane lake and a liquid one would look identical. The team needed spectroscopy, thermal data, repeat passes to check for changes. They had circumstantial evidence, not proof. The October pass mapped 1% of Titan's surface. The dark regions stretched across hundreds of kilometers, far larger than any liquid body hypothesized before Cassini arrived. If they were lakes, Titan wasn't just wet, it was drenched. 3 months later, Huygens would settle the question in the most dramatic way possible. On January 14, 2005, Huygens separated from Cassini and plunged into Titan's atmosphere at 6 kilometers per second. For 2.5 hours, it fell through the orange haze, parachutes deploying in stages, cameras clicking every few seconds. The first images came back blurred, almost abstract, but as the probe dropped lower, the shapes sharpened into something unmistakable. Branching channels carved into the highlands, flowing downhill like river networks on Earth. Dark plains spreading across the lowlands, their surfaces smooth and featureless. And scattered across those plains, thousands of rounded pebbles, 10 to 15 centimeters across, worn smooth like stones in a riverbed. At 1,270 meters altitude, Huygens hit the surface at 4.5 meters per second. The impact sensor registered something with the consistency of wet sand, firm but yielding. The probe settled, tilted 3 degrees, and kept transmitting. But the real shock came when scientists analyzed what those rocks were made of. Spectroscopy readings came back unambiguous. The pebbles weren't rock at all. They were water ice, frozen solid at minus 179 degrees Celsius, harder than granite at that temperature. On Titan, water doesn't flow, it builds mountains. The sand, turned out to be organic sediment, hydrocarbon particles that had settled out of the atmosphere over millions of years, piling up in drifts and dunes. Huygens gas chromatograph detected methane humidity rising as the probe descended, climbing from 45% at altitude to nearly 50% near the surface. Active evaporation, happening in real time. The pebbles showed signs of erosion, their surfaces smoothed by something that flowed and tumbled them. The channels had carved through highlands and emptied into basins. Everything pointed to a hydrological cycle, but running on methane instead of water, at a temperature where Earth's oceans would be solid ice. If methane was evaporating, that meant liquid methane was somewhere nearby, and Cassini's radar was about to find it. On June 6, 2005, Cassini's radar swept across Titan's southern hemisphere and locked onto a feature 235 kilometers long, kidney-shaped, darker than anything around it. The radar return was almost zero. Something down there was swallowing the signal. The team named it Ontario Lacus, after the Great Lake. Its edges were sharp and smooth, no roughness, no texture, liquid. The radar properties matched laboratory measurements of liquid ethane and methane, mixed together at -179 degrees Celsius. Not a dry lakebed, not a mirage, an actual lake sitting on the surface right now. Ontario covered about 15,000 square km, roughly the size of Lake Ontario itself. Subsequent passes showed subtle changes in its shoreline, hints that the liquid level might be rising or falling with the seasons. But something felt off. Titan is 50% larger than Earth's moon. A lake this size should be common if the methane cycle worked the way models predicted. But Ontario was tiny compared to what Cassini would discover when it turned its radar toward the North Pole. In 2006, Cassini's radar swept across Titan's North Pole. The data showed dozens of dark, smooth patches clustered at high latitudes. They weren't small. The three largest features dwarfed Ontario Lacus. Kraken Mare stretched 1,170 kilometers from end to end. Ligeia Mare measured 420 kilometers across. Punga Mare, the smallest of the trio, still covered 380 kilometers. For comparison, Lake Superior is 563 kilometers long. Kraken Mare was nearly twice that. The radar returns showed liquid hydrocarbons pooled in basins that looked carved, not random. All told, the northern seas held more liquid methane and ethane than all of Earth's proven oil and gas reserves. Kraken Mare alone was larger than the Caspian Sea, but the truly inexplicable part was what wasn't there. Titan is 4 billion years old. Its surface should be pockmarked with impact craters, like the Moon or Mercury. But Cassini's imaging revealed fewer than 60 confirmed craters across the entire Moon. Earth's moon has hundreds of thousands. Even Mars, with its thin atmosphere, has over 600,000 catalogued impacts. Larger than 1 kilometer's Titan's crater count was statistically impossible unless something was erasing them. The options were limited. Rainfall could erode rims over millions of years. Lakes could fill old basins, hiding the scars. Or tectonic activity, cryovolcanoes, or sediment deposition could bury them entirely. Each explanation pointed to the same conclusion. Titan's surface wasn't static. It was resurfacing itself on geologically recent timescales, maybe within the last 100 million to 1 billion years. And if Titan's surface was active, that meant weather, real weather, with storms, clouds, and seasons. Titan's methane cycle works like Earth's water cycle, just 200 degrees colder. Methane evaporates from the northern seas when summer sunlight hits them. It rises into the atmosphere, cools, and condenses into clouds at altitudes around 20 kilometers. Those clouds drift south or north depending on the season. When conditions align, methane rain falls. Cassini's spectrometer measured droplet sizes around 1 to 5 millimeters, roughly the size of drizzle on Earth. The rain carves channels into Titan's icy crust, creating river networks that snake toward the poles. Some channels stretch 400 kilometers, longer than the Thames. They drain into the seas, completing the loop. One Titan year lasts 29.5 Earth years, so each season drags on for 7 Earth years. That means slow, patient evaporation in one hemisphere while the other sits locked in winter. The first direct evidence of rainfall wouldn't come from radar. It would come from watching the ground itself change color. In 2010, Cassini's infrared spectrometer caught something new. Dark patches materialized near the equator, appearing within hours of cloud activity overhead. The patches spread across several hundred square kilometers, then slowly faded over the next few weeks. The timing wasn't coincidence. These were wet surfaces, methane-soaked regolith reflecting less infrared light than the surrounding dry terrain. The liquid was either evaporating back into the atmosphere or seeping down through porous surface material. Either way, this was the first direct observation of active precipitation on another world. The patches never formed stable bodies of liquid. The equatorial heat, even at 94 K, was enough to keep methane from pooling. Rain would fall, soak in, then vanish within a Titan month. It confirmed the weather models. The methane cycle was real and operating across the entire moon. But if rain was falling at the equator, why were all the lakes concentrated at the poles? The first comprehensive maps made it obvious. Titan's North Pole was crowded with hundreds of lakes, some small as ponds, others stretching 100 kilometers across. The South Pole had only a handful. Ontario Lacus, the largest southern lake, sat alone in a region that should have mirrored the North's liquid abundance. The explanation required thinking in Titan years, not Earth years. When Cassini arrived in 2004, it was winter in the north and summer in the south. The northern lakes were full, locked under cold darkness. The south was warm, evaporating its reserves. Over the mission's 13-year span, the seasons flipped. Southern summer began its slow retreat, and autumn crept across the northern hemisphere. If the model held, the atmospheric methane evaporating from the south should condense and rain down in the north, refilling those lakes as winter approached. The asymmetry wasn't permanent, it was seasonal, a slow sloshing of methane from pole to pole over decades. If that hypothesis was correct, Cassini should eventually see the lakes changing, and in 2012, it did. Ontario Lacus shrank. Radar passes in 2005 showed a lake roughly 235 kilometers across. By 2009, the shoreline had pulled back measurably. Altimetry data revealed the liquid level had dropped by at least 4 meters, maybe more. The southern summer was draining it in real time. The methane wasn't disappearing, it was evaporating, rising into the atmosphere, drifting north with the circulation patterns. As the north warmed into spring, clouds began forming over the polar seas. Rainfall picked up. The cycle was completing, liquid transferring from one hemisphere to the other across a span longer than most human careers. The observations confirmed the seasonal model. Titan's lakes were migratory, oscillating between poles over a 29.5-year orbit. Ontario Lacus would keep shrinking until southern winter returned decades later. By then, the northern seas would be evaporating, sending their methane back south. But there was one lake in the north that wasn't following the pattern at all. Ligeia Mare sits at 78 degrees north, a sea of liquid methane 420 kilometers across. Cassini watched it through 6 Titan years. Ontario shrank by 30%. The northern seas should have been filling as southern summer ended. Ligeia didn't move. Radar altimetry showed the same shoreline in 2007 and 2017. Spectrometry confirmed the composition: 71% methane, dissolved nitrogen, trace ethane. The depth readings held constant at 160 meters near the center. Whatever fed Ligeia was keeping pace with evaporation to the millimeter. Models predicted a 5-meter drop over a single summer. Ligeia showed zero net change. Either it was connected to a subsurface reservoir massive enough to buffer seasonal swings, or something was refilling it at the exact rate it lost liquid. Both options demanded geology Titan wasn't supposed to have. And in 2013, Cassini would detect something on Ligeia's surface that shouldn't have been there. The T-92 flyby on April 26, 2013, caught a bright radar return in Ligeia's southwestern corner. The patch covered 75 square km. Previous passes over that exact coordinate showed only dark liquid. Cassini's radar saw smooth surfaces as dark, rough ones as bright. Open methane shouldn't light up. The feature persisted through the next 3 flybys. Then it vanished. Engineers checked for instrument glitches. The signal was real. The press called it Magic Island. Scientists proposed 4 mechanisms: nitrogen bubbles rising from the depths, surface waves driven by wind, rafts of floating organics, or suspended solids churning the liquid. Each hypothesis had problems. Titan's winds measured 0.5 meters per second at the surface, too weak to generate radar-bright waves. Bubbles should have dissipated in hours, not months. Floating solids needed densities between liquid methane at 0.45 grams Sui and the composition of Titan's crust, a narrow window. Suspended organics could work, but required a mixing event powerful enough to stir 160 meters of liquid. Before scientists could solve the Magic Island mystery, Cassini would find something even stranger in Kraken Mare. Kraken Mare spans 400,000 square km, larger than the Caspian Sea. Radar altimetry measured depths exceeding 160 meters through most of the basin. One sounding hit 300 meters before losing the return signal. That made Kraken deeper than Superior, deeper than any lake on Earth, filled not with water but liquid methane at 94 K. Spectrometry revealed a different composition than Ligeia. Kraken held more ethane, up to 40% in the northern arms, with methane dominant in the south. Dissolved nitrogen saturated both. The liquid's density varied by basin, 0.45 to 0.52 grams per cubic centimeter. Cassini's microwave radiometer detected thermal stratification, warmer liquid at depth, colder near the surface, stable for years. A sea this deep required either a basin carved by some colossal erosion event or tectonic subsidence on a moon that wasn't supposed to have active plates. The volume of liquid exceeded 9 times all the hydrocarbon deposits Earth has ever burned. Kraken alone held enough methane to supply Titan's atmospheric losses for 30 million years, if the liquid could somehow reach the air. But the depth wasn't the puzzle. It was the bright streaks that appeared along Kraken's northern shoreline. In images taken 16 days apart, bright patches appeared on Kraken's surface that hadn't been there before. They glowed in radar, then faded, then reappeared elsewhere. Cassini tracked 5 separate events between 2013 and 2015, each lasting hours to weeks. The patches weren't fixed to the shoreline. They drifted. One hypothesis said wind was raising waves tall enough to scatter radar differently than calm liquid. But Titan's thick atmosphere and low gravity meant waves should propagate slowly, taking days to cross the distances these features moved in hours. Another model proposed bubbles, nitrogen or methane gas released from vents in the lake floor could foam to the surface and change the radar signature. Lab experiments showed that organic compounds dissolved in liquid methane form stable foams under the right pressure and temperature. The foam would float, drift with currents, then collapse when the gas escaped. But bubbles required a source. If gases were venting from below, that raised a terrifying question: what was generating them? Cassini's gravity instrument measured how Titan's shape deformed as Saturn's tidal forces squeezed it during each orbit. The moon bulged by up to 10 meters, then relaxed. That degree of flexing was impossible for a solid body. Something beneath the crust had to be liquid. The data pointed to a global ocean 50 to 100 kilometers below the surface, likely water mixed with ammonia to stay liquid at temperatures near 176 K. The ammonia acted as antifreeze, dropping the freezing point low enough to persist in Titan's cold interior. The ocean was estimated to be 200 to 300 kilometers deep, dwarfing the surface seas. This wasn't unique. Europa, Enceladus, and Ganymede all hid subsurface oceans. But Titan's was different. The overlying ice shell showed signs of stress, cracks that suggested the crust wasn't a static barrier. Heat from tidal flexing and radioactive decay in Titan's core could warm pockets of the ice, thinning it in places. That ocean had been isolated from the surface for billions of years, or so scientists thought. Radar and infrared scans identified more than a dozen features that didn't fit the profile of impact craters or dunes. They were circular domes, some over 100 kilometers wide, with flow patterns radiating outward. The structures resembled shield volcanoes, but the flows weren't lava, they were ice. One site, Sotra Patera, showed a 1,500-meter-high dome next to a 1,800-meter-deep pit. Spectral analysis revealed fresh ice on the dome's slopes, brighter and less contaminated by organics than the surrounding terrain. The pit's depth and the dome's height suggested material had erupted from below, then collapsed inward after the reservoir emptied. The flows were cryolava, a slurry of water, ammonia, and methane that behaved like molten rock at Titan's surface temperature. Lab simulations showed this mixture could erupt explosively if pressurized pockets in the ice shell suddenly breached. The ammonia lowered the melting point, keeping the slurry fluid long enough to travel kilometers before freezing solid. If water from the deep ocean was reaching the surface, it could be mixing with surface methane and producing something unexpected. Cassini's ion and neutral mass spectrometer wasn't just detecting methane. During dozens of flybys through Titan's upper atmosphere, it found benzene, toluene, propane, ethylene, acetylene. By 2008, the instrument had catalogued over 100 distinct organic compounds, many of them polycyclic aromatics, with ring structures of carbon atoms locked together. UV radiation from the sun was shattering methane molecules at altitudes above 900 kilometers, freeing carbon and hydrogen radicals that recombined into larger and larger chains. Nitrogen from the atmosphere was getting incorporated too, forming nitriles and amines. This wasn't just chemistry. It was a prebiotic factory assembling the molecular building blocks found in living cells, running continuously for billions of years. The heavier molecules couldn't stay airborne. They clumped together, forming aerosol particles that drifted downward through the haze layers like microscopic snow. Cassini's cameras watched this orange fog thicken below 200 kilometers, where temperatures dropped low enough for the organics to condense into solid grains. But the most complex organics weren't floating in the atmosphere. They were settling on the surface as a tarry sludge. In the 1970s, Carl Sagan's team bombarded methane and nitrogen gas with UV light in a lab chamber and got a reddish-brown gunk coating the walls. They called it tholin, from the Greek word for muddy. Titan's entire atmosphere is a tholin reactor, converting simple gases into complex polymers that rain down as sticky sediment. Spectroscopic analysis showed tholins contain hundreds of bonded carbon, hydrogen, and nitrogen atoms arranged in branching networks. Some molecules weighed over 8,000 atomic mass units. They're responsible for Titan's orange color, absorbing blue and green light while scattering red wavelengths back into space. On the surface, they accumulate as a layer of organic tar mixed with water ice grains. Cassini's visual and infrared mapping spectrometer detected tholin signatures across Titan's equatorial dune fields, where the particles appeared to coat sand grains like a varnish. Near the poles, the infrared absorption bands looked different. Something was altering the tholin's chemistry. In 2014, lab experiments would reveal that tholins behave very strangely when mixed with liquid methane. Researchers at NASA's Jet Propulsion Laboratory synthesized tholins identical to Titan's, cooled a chamber to 94 K, and poured in liquid methane. The tholins didn't dissolve. They didn't sink either. They formed a colloidal suspension, tiny particles hovering in the liquid like dust motes caught in a sunbeam, stable for hours. When they agitated the mixture, it turned opaque. When they let it settle, clarity returned, but slowly. The particles carried electrostatic charges that kept them from clumping, and methane's low viscosity meant sedimentation rates were glacially slow. At 1.5 Earth atmospheres of pressure and Titan's gravity, a 10-micron tholin particle would take 3 days to sink 1 meter. This could explain the Magic Island's appearance and disappearance. It could explain the transient bright features Cassini's radar spotted in Ligeia Mare. A methane rainstorm dumps fresh tholins into a lake, the turbulence suspends them, and radar sees a cloudy patch that fades over weeks as the organics slowly settle. But if tholins were suspended in the lakes, they would eventually sink, and Cassini's radar was about to find where they went. In 2013, Cassini's radar did something no instrument had ever done. It penetrated the surface of Ligeia Mare and bounced back from the bottom, 170 meters down. The echo revealed layers, stacked like pages in a book. Each layer was a different density. The top was liquid methane and ethane. Below that, a denser sludge of dissolved organics. And at the very bottom, a solid floor of compacted tholins that had been raining down for thousands of years. Kraken Mare showed the same structure, but the sediment was thicker. In some places, the organic muck was over 200 meters deep. That's not a decade of accumulation. That's millennia of Titan's atmosphere slowly settling into the lakes, molecule by molecule. The discovery of sediment layers meant the lakes had histories, and one lake would reveal a history millions of years long. Cassini's radar scans found something else. Scattered across Titan's northern plains were hundreds of smooth-floored depressions, each one perfectly round or oval, each one empty. They had the exact shape of the filled lakes, but no liquid inside. The edges were sharp and well-defined. The floors were flat and radar bright. These weren't craters. They were fossil lake beds, ghosts of seas that had existed tens of thousands of years ago when Titan's climate was wetter. Ontario Lacus, the largest lake in Titan's southern hemisphere, appeared to be shrinking. Cassini watched its shoreline recede by several kilometers between 2005 and 2010. The lake was evaporating in real time, carving a new fossil into the landscape. If the lakes had dried up, where did all that methane go? The answer was written around the edges. Every dry lake bed had a bright rim, sometimes 10 kilometers wide, that radar lit up like a flare. The rims were solid, flat, and chemically distinct from the surrounding terrain. They looked exactly like the Bonneville salt flats in Utah. When a lake evaporates, dissolved minerals are left behind. On Earth, it's halite and gypsum. On Titan, it should be frozen benzene, acetylene, butane, complex nitriles, things that dissolve in liquid methane and crystallize when it boils away. But Cassini's spectrometers couldn't identify them. The infrared signatures were muddy, overlapping. Nothing matched the lab data. Every evaporite candidate absorbed light in slightly the wrong wavelengths. The bright rims were made of something, but no one could say what. And in 2015, Cassini found a lake bed that held the answer. Sotra Patera sits near Titan's equator, a shallow basin 30 kilometers wide. When Cassini's radar passed over it in 2007, the return signal spiked. The lake bed wasn't scattering the radar like rough terrain. It was reflecting it back like a mirror. Specular reflection requires a surface smoother than the radar wavelength, polished to within a few millimeters. On Earth, only liquids and freshly solidified lava produce that kind of finish. Sotra's floor gleamed under radar like polished glass, and the only explanation was a coating of crystalline material. 3 candidates emerged. Benzene freezes at 5.5 degrees Celsius and forms hexagonal crystals. Butane solidifies at 138 degrees Celsius below zero into a waxy lattice. Acetylene, stable at 81 degrees Celsius below zero, grows needle-shaped grains that pack flat. All 3 could theoretically coat a lake bed if the methane evaporated slowly enough. But spectroscopy ruled them out one by one. Benzene absorbs at 3.3 microns, butane at 3.4, acetylene at 3.0. Sotra's signature sat at 3.1 microns with a secondary peak at 13.7, matching none of them. The coating was real, but it wasn't organic frost. But none of those materials explained why the coating was so perfectly smooth, unless something had melted it. In 2010, a team led by Geoffrey Moore proposed Sotra Patera wasn't a lakebed at all. It was a caldera. The basin sat at the center of a 1,500-meter-high dome, flanked by lobed flows that extended 60 kilometers downslope. The flows showed up bright in radar, meaning they were rough, fractured, and geologically young. Moore's hypothesis was cryovolcanism. Titan's subsurface ocean, pressurized by 100 kilometers of ice, could force water-ammonia slurries up through fractures in the crust. When the mixture breached the surface, it would freeze almost instantly at 179 degrees Celsius below zero, forming a lumpy, broken flow. The caldera floor, meanwhile, would be a frozen lake of cryolava, polished smooth as it solidified. Ammonia lowers water's freezing point to 97 degrees Celsius below zero, keeping the mixture liquid long enough to flow. The spectral signature at 3.1 microns matched water ice contaminated with ammonia and dissolved organics. If Moore was right, Sotra Patera was Titan's first confirmed cryovolcano, and the bright rims around other lake beds were ammonia evaporites left behind when the lava froze. But cryovolcanoes need a heat source, and Titan's core should have frozen solid 4 billion years ago. Tidal flexing from Saturn generates some warmth, but models predicted only 0.1 watts per square meter, not enough to melt ice at depth, proving it would require detecting heat, and in 2016, Cassini's infrared instrument found something glowing. VIMS, Cassini's visual and infrared mapping spectrometer, scanned Sotra Patera in wavelengths between 0.35 and 5.1 microns. At 5 microns, thermal emission dominates reflected sunlight, letting VIMS measure surface temperature. Most of Titan reads 94 K, locked at equilibrium with the weak sunlight. Sotra's caldera floor read 97 K. 3 degrees doesn't sound like much, but at 94 K, molecular motion nearly stops. A 3% temperature increase means 12% more thermal energy, easily detectable against the background. The hotspot was 8 kilometers wide, centered on the caldera, and it didn't correlate with topography or albedo. It was coming from below. VIMS detected 2 more anomalies near Sotra, each 2 to 4 degrees warmer than the surroundings. One sat on a flow lobe 40 kilometers west, the other aligned with a chain of collapse pits stretching north from the caldera. All 3 hotspots were faint, barely above the noise floor, and they faded between flybys. If they were real, they weren't constant. No one expected active volcanism on a moon this cold, but the alternative was worse. If the hotspots were instrument artifacts, then Sotra's smooth floor, its spectral signature, and its dome and flow morphology were just coincidences. The data pointed one way. If Sotra was volcanically active, it could be venting methane directly into the atmosphere, solving the methane replenishment paradox. The cryovolcanism hypothesis was elegant. Methane venting from Sotra and other active sites could replace what sunlight destroyed. But the numbers didn't close. Even if every suspected hotspot was erupting, the volume wasn't enough to sustain 1.4% atmospheric methane over billions of years. The second hypothesis looked to the crust. Methane clathrates, ice cages trapping methane molecules, could be buried kilometers down. Tidal flexing or internal heat might destabilize them, releasing bursts of gas. But clathrates require specific pressure and temperature windows, and Cassini's subsurface radar showed no widespread reservoirs. The third option was recycling. Photochemistry breaks methane into heavier organics, which rain out and eventually decompose back into methane. It's a closed loop, except it's not perfectly closed. Some carbon locks into solid polymers, some gets buried in lake sediments. The leak rate is small, but over geologic time it's fatal. No single source worked. The math required a combination, or something no one had modeled yet. But there was a fourth possibility no one had seriously considered, until Cassini measured the methane's isotopes. Deuterium is hydrogen's heavier cousin, 1 proton plus 1 neutron. It's rare, but not uniformly rare. Comets have high deuterium to hydrogen ratios because they formed in the cold outer solar system. Primordial methane, locked in Titan's interior during accretion, should match that signature. Cassini's mass spectrometer sampled atmospheric methane at multiple altitudes. The D to H ratio came back depleted, not slightly off, detectably lower than cometary or solar nebula values. If the methane was original, left over from Titan's formation 4.5 billion years ago, the isotopes should have been heavier. The only way to deplete deuterium is to cycle methane through processes that preferentially lose the heavy isotope. Photolysis in the upper atmosphere strips deuterium faster than regular hydrogen, but that enriches the remaining methane. It doesn't deplete it. The depletion pointed inward, not upward. The methane wasn't ancient, and it wasn't cometary. It had been through Titan's interior multiple times, stripped and reconstituted by chemistry that left an isotopic fingerprint. That meant methane wasn't being passively released. It was being actively processed deep inside the moon. On Earth, there's a reaction that turns rock into methane: serpentinization. When water seeps through ultramafic rock, olivine and pyroxene, rich in iron and magnesium, it oxidizes the minerals. The oxygen binds to the rock. The hydrogen is freed, and at the right temperatures, it combines with carbon dioxide or carbon monoxide to form methane. It powers Lost City, a hydrothermal vent field 800 meters down in the mid-Atlantic, where 90 degrees Celsius alkaline fluids pour out of white carbonate chimneys. No magma, no volcanic heat, just water and rock reacting exothermically. The methane and hydrogen it produces support ecosystems that never see sunlight. Titan has the ingredients. A subsurface ocean 100 kilometers deep sits atop a rocky core, likely rich in silicates. If water percolates down through fractures, reaching hot rock at the ocean core boundary, serpentinization could run continuously. The reaction doesn't care if the surface is 94 K. Deep inside, pressure and residual radiogenic heat provide the energy. The isotopic depletion fit. Serpentinization produces methane with a lighter D to H signature because the hydrogen comes from water that's been thermally processed, not from primordial ice. If serpentinization was happening inside Titan, the subsurface ocean wasn't just water, it was a chemical reactor. Planetary scientists started modeling the heat budget. Titan's core contains radioactive elements, potassium-40, thorium-232, uranium-238. Over 4.5 billion years they've been decaying, pumping heat into the interior at a rate of roughly 6 to 8 gigawatts. That's enough to keep the base of the subsurface ocean above 273 K, maybe 280 K in localized zones. Water at that temperature, in contact with a silicate core, drives hydrothermal circulation. Hot fluid rises, cold fluid sinks, minerals dissolve and precipitate. On Earth, hydrothermal vents create chemical gradients. Reduced compounds meet oxidized seawater. Energy flows. Life thrives in the boundary. Titan's ocean might have the same structure, a warm alkaline layer near the core, a colder ammonia-rich layer above, chemistry happening at the interface. And in 2017, Cassini would detect molecules in the atmosphere that could only come from that deep ocean. The ion and neutral mass spectrometer picked up signals above 100 atomic mass units, benzene derivatives, polycyclic aromatics, nitrogen-heavy rings. These molecules are too massive to assemble in the ionized chaos of the upper atmosphere, where UV radiation tears apart anything complex. Formation pathways require sustained chemistry, the kind that happens in dense gas or liquid. The lower atmosphere could do it. aerosol particles coalescing in the orange haze, methane and nitrogen reacting over centuries. The surface lakes could do it, organics concentrating as ethane evaporates. But the distribution was wrong. The heaviest molecules appeared at altitudes where they shouldn't persist. They should sink, raining out within weeks. Instead, they lingered, replenished from somewhere. The leading explanation was that they formed in the lower atmosphere or on the surface, but one scientist proposed they came from below. A 2017 paper in Icarus argued for cryovolcanic plumes. If the subsurface ocean was venting through cracks in the ice shell, it could inject water vapor, ammonia, and dissolved organics directly into the stratosphere. Enceladus does this constantly. Geysers shooting 250 kilometers high, seeding Saturn's E-ring with ice grains and complex molecules. Titan's plumes would be weaker, maybe intermittent, but the principle holds. Pressure builds in subsurface reservoirs, ice fractures, material erupts. The organics wouldn't survive intact. Radiation would shred them on the way up, but the fragments would recombine into the heavy species Cassini detected. Most scientists stayed skeptical. Titan's ice shell is thicker than Enceladus's, maybe 100 kilometers, compared to 30 kilometers. Tidal heating is weaker. No one had spotted an active plume in infrared or imaging data. The atmosphere's methane could explain everything without invoking subsurface sources. But in 2018, Cassini's final data would force them to reconsider. That reconsideration started with a molecule almost nobody was watching for. Sifting through radio data from the ALMA array in Chile, researchers pulled out a clear signal for vinyl cyanide, C2H3CN, floating in Titan's haze. The estimated abundance was enormous, enough to seed the lakes below with a steady drizzle of the stuff. Vinyl cyanide sounds like an odd candidate for anything hopeful, but run it through a computer model of liquid methane at 94K, and something strange happens. The molecules line up, tails in, heads out, and fold themselves into tiny hollow spheres. On Earth, water and fatty lipids do that dance to build every cell membrane you're made of. Titan has no liquid water, so that chemistry should be impossible. Yet vinyl cyanide seems to pull off the same trick in a solvent 180 degrees colder than your freezer. If vinyl cyanide was raining into the lakes, it could be forming protocell membranes right now. A team at Cornell gave these hypothetical spheres a name. They called them azotosomes, from the French word for nitrogen, because their skins are stitched together from nitrogen-bearing organics instead of the oxygen and phosphorus lipids we rely on. In their simulations, the vesicles held together with roughly the same stability a soap bubble membrane shows in water. Think about what that means. A membrane is the first thing life needs, a wall that separates inside from outside, that keeps the good chemistry in and the chaos out. Every cell on Earth is basically a bag of reactions wrapped in a lipid skin. The Cornell work suggested Titan might supply that same starter kit, using totally alien ingredients, no water required. It's a blueprint for a second, independent way to build a living thing. But proving life exists in Titan's lakes would require detecting metabolic activity, and no instrument has ever been designed to do that. Then Cassini handed scientists a number that wouldn't sit still. High in the atmosphere, sunlight breaks methane apart and produces hydrogen, which should drift downward and build up near the ground. Instead, the models showed hydrogen streaming toward the surface and simply vanishing there. The flow rate was about 10,000 trillion molecules per square centimeter every second, and at the surface, it dropped close to zero. Something was swallowing it. No obvious chemistry on a frozen crust of ice and organics should pull hydrogen out of the air that fast. Back in 2005, astrobiologist Chris McKay had predicted exactly this signature. He argued that if methane-based life were breathing on Titan, it would inhale hydrogen and eat acetylene as fuel, stripping both from the surface. If organisms were metabolizing hydrogen and acetylene in the lakes, they would deplete both gases at the surface, and that's exactly what Cassini saw. The acetylene problem ran deeper than anyone expected. Photochemistry models predicted the compound should rain down continuously, building up in thick layers across Titan's surface. Instead, Cassini's instruments detected almost none of it. Three explanations emerged. First, acetylene might dissolve readily in liquid methane and ethane, sinking into the lakes where instruments couldn't see it. Second, eons of rainfall could have buried it under meters of organic sediment, effectively removing it from the active cycle. Or third, something was consuming it faster than it accumulated. The hydrogen depletion pointed in the same direction. Both signatures matched the metabolic waste stream of an organism that ate acetylene and breathed hydrogen, excreting methane as a byproduct. The methanogen hypothesis was compelling, but it had one major problem. Titan's surface sits at -179 degrees Celsius, cold enough to freeze nitrogen solid. At that temperature, the chemical reactions that drive terrestrial metabolism slow to a crawl. Enzymes that catalyze life's processes on Earth would be locked in place, their molecular machinery grinding to a halt. The numbers are brutal. Reaction rates typically halve for every 10 degrees Celsius drop in temperature. Between Earth's average and Titan's lakes, that's a 194 degrees Celsius gap. Run the math and biochemical reactions become trillions of times slower, turning metabolic timescales from milliseconds to geological epochs. For life to function in liquid methane, it would need fundamentally different chemistry, not just adapted proteins, but catalysts that retain flexibility and activity near absolute zero. Molecules that could shuttle electrons and break chemical bonds while immersed in a solvent 90 degrees Celsius colder than liquid nitrogen. And in 2019, a lab experiment would demonstrate that such enzymes might actually exist. A team at NASA's Jet Propulsion Laboratory set out to test whether organic catalysts could survive cryogenic conditions. They synthesized a class of molecules called acetylene compounds, carbon-based structures with reactive sites capable of shuttling electrons between donor and acceptor molecules. Then they dropped the temperature to -196 degrees Celsius, submerging the catalysts in liquid nitrogen. The molecules didn't freeze, they didn't shatter. Instead, they continued to facilitate redox reactions, the fundamental electron transfer chemistry that powers metabolism. The reaction rates were slow by terrestrial standards, thousands of times slower than in water at room temperature. But they were measurable, repeatable, and fast enough to support a metabolic cycle over hours or days rather than millennia. The experiment proved cryogenic biochemistry wasn't just theoretically possible, it was chemically viable. But even if life could survive in the lakes, it couldn't have originated there, because the lakes are too young. Cassini's radar measured sediment layers at the bottom of Ligeia Mare and Kraken Mare. The accumulation rates pointed to something startling. Those northern basins filled within the last 500,000 years, maybe less. That's a blink in geological time. Titan is 4.5 billion years old, but its largest lakes are younger than Homo sapiens. If methane-based life exists in the lakes today, it couldn't have evolved there. The timescales don't match. Cryogenic metabolism might work on the scale of days, but abiogenesis, the jump from chemistry to biology, takes millions of years minimum. The lakes are too young for origin events. That means life would have had to originate somewhere older, somewhere stable, and then colonize the lakes when they appeared. But where? The atmosphere's been there for billions of years, but it's too thin and reactive. The surface gets scoured by cosmic rays. The most likely origin site wasn't the surface at all, it was the subsurface ocean. The subsurface ocean sits 50 to 80 kilometers below Titan's crust, liquid water kept warm by tidal flexing and radiogenic heat. It's been stable for billions of years. If serpentinization is happening down there, you'd have hydrothermal vents, chemical gradients, energy sources, the same setup that likely sparked life on Earth. Water-based biochemistry could have taken root in that ocean long before the surface lakes ever existed. Now picture cryovolcanism punching through the ice shell. Warm water and organics erupt onto the surface, freeze, mix with methane rain, wash into the lakes. You'd have a conduit between two totally separate chemical environments. That's the dual biosphere hypothesis. Water-based life below, methane-based life above, connected by geological plumbing. Surface organisms could be feeding on organic material synthesized in the ocean and delivered by eruptions. Or the exchange could go both ways. Atmospheric organics seeping down through cracks, feeding chemotrophs in the ice. Two trees of life, two solvents, one moon. If both biospheres existed, Titan would be the only body in the solar system with two independent origins of life. But proving it would require a lander. NASA's Dragonfly mission launches in 2028 and arrives at Titan in 2034. It's not an orbiter, it's a quadcopter the size of a car, powered by a radioisotope thermoelectric generator built to fly. Titan's thick atmosphere and low gravity make flight easier there than on Earth. Dragonfly will cover hundreds of kilometers, hopping between sites, sampling surface organics, drilling into the regolith, running mass spectrometry on the spot. Its primary mission is to search for prebiotic chemistry and biosignatures, the chemical fingerprints life would leave behind. It'll measure isotope ratios, look for chirality in organic molecules, test for metabolic byproducts like the hydrogen and acetylene depletions Cassini hinted at. If methane-based life exists, Dragonfly is designed to find it. The mission baseline is 2.7 years on the surface, but if the RTG holds up, it could fly for a decade. It'll image terrain Cassini never resolved, map seasonal changes, maybe even witness a cryovolcanic eruption in real time. But Dragonfly won't land near the lakes. It will land in an equatorial dune field, and there's a reason for that. Titan's equator is buried under dune fields that stretch for thousands of kilometers. These aren't beaches, they're organic deserts. Cassini's radar mapped longitudinal dunes running parallel to the prevailing winds, some of them 100 meters tall and a kilometer wide. The grains aren't silica, they're hydrocarbon particles, coated tholins, maybe ice fragments bound together by tarry polymers. Wind speeds at the surface are sluggish, around 1 meter per second most of the year, but during equinox storms, they spike enough to lift and shape these mountains of grit. Radar suggests the dunes aren't uniform. Some regions show bright subsurface returns that could be clathrate lenses or pockets of water ice mixed into the organics. Each layer records a snapshot of atmospheric chemistry, precipitation patterns, maybe even methane floods that swept through millennia ago. Dragonfly will land in Shangri-La, the largest dune field on Titan, because it's geologically accessible and scientifically dense. The dunes aren't just sand, they're a library of Titan's organic history, layer by layer. Within flight range of Shangri-La sits Selk Crater, a 90 kilometers impact scar that punched through the crust around 1 billion years ago. The kinetic energy would have been catastrophic. Surface ice vaporized instantly, subsurface water erupted as steam, and for a brief window, the crater floor was a hydrothermal cauldron. That's the prize. Impact craters on Titan are natural mixing chambers where liquid water from below meets organic haze from above. Temperatures inside Selk might have stayed above freezing for thousands of years, long enough for amino acids to form, for nitriles to hydrolyze, for chemistry that never happens in the frozen lakes. Cassini's radar shows Selk's rim is still distinct, the ejecta blanket spread out in radial streaks. Dragonfly will hop across that debris field, sampling material thrown up from depth, looking for mineralogical signatures of aqueous alteration and complex carbon chains. If prebiotic reactions occurred at Selk, Dragonfly should find amino acids, nucleobases, or other biomolecule precursors in the crater ejecta. Dragonfly's main instrument is DRAMS, the Dragonfly Mass Spectrometer. It's a compact time-of-flight system that can resolve molecules up to 2,400 atomic mass units, sensitive enough to detect trace organics at parts per billion. The drill punches 10 centimeters into the surface, pulls up a sample, heats it in stages up to 600 degrees Celsius, and ionizes the vapor. The mass spectrum tells you what's there. Methane, ethane, propane show up as clean peaks. Nitriles, aldehydes, carboxylic acids each have distinct signatures. If there are amino acids, even at low concentration, DRAMs will see them. If there are polymers or macromolecules, the pyrolysis fragments will hint at their structure. The mission profile calls for sampling at multiple sites, comparing dune interiors to crater ejecta to potential shoreline deposits. Each dataset builds a map of organic diversity across terrain types. If lifelike chemistry exists, it'll show up as compositional anomalies, molecular patterns that don't fit abiotic synthesis. But the most important measurement Dragonfly will make isn't chemical, it's seismic. Dragonfly's body houses 3 seismometers, each oriented along a different axis. They'll listen for Titan quakes, tremors caused by tidal flexing, as Saturn's gravity kneads the Moon's interior every 16 days. The seismic waves travel at different speeds through ice, liquid water, and rock, so their arrival times map the interior like an ultrasound. If the ice shell is 80 kilometers thick, as models suggest, quakes will be rare and shallow. If it's 20 kilometers thick, you'd see frequent deep events as the ocean sloshes against the shell from below. The instruments can detect vibrations smaller than a nanometer, sensitive enough to pick up distant impacts or cryovolcanic venting. Cassini found hints of tidal dissipation, meaning Titan's interior is losing heat through friction. Seismology will measure how much. A highly active interior would mean constant resurfacing, fresh organics cycled from the ocean, and a heat source that could sustain chemistry for billions of years. If the ice shell is thin and actively fracturing, it could mean the subsurface ocean is closer to the surface than models predict and more accessible to future missions. After Dragonfly, the next mission concept is an orbiter carrying ice-penetrating radar. The instrument would fire 60 MHz pulses through Titan's crust, mapping the boundary between ice and liquid water with 10 meters vertical resolution. You'd see the ocean's topography, thickness variations, and any subsurface voids where melt has pooled. Radar has already mapped Europa's ice shell and found double ridges, chaos terrain, and possible brine lenses. On Titan, the target is cryovolcanic conduits, channels where liquid from the ocean has pushed upward and frozen partway through. These would appear as radar-bright columns cutting through the shell, potential drilling sites where the ice is thinnest. The orbiter would also measure the shell's dielectric constant, which reveals how much ammonia or salts are mixed into the ice. Pure water ice is transparent to radar. Salty ice scatters the signal. If you see bright reflections at shallow depths, it means conductive material, possibly brine pockets or organic-rich layers. The data would guide a future lander to a spot where drilling 5 kilometers gets you to liquid instead of 50 kilometers. But the mission scientists really want to fly is a submarine. The proposal is called the Titan Mare Explorer, a 6 meters autonomous sub designed to survive in liquid methane at -179 degrees Celsius. It would splash down in Kraken Mare, the largest sea, and spend 90 days mapping the floor with sonar and side-scan imaging. The lake is at least 300 meters deep in places, maybe deeper, and no one knows what's down there. The sub carries a mass spectrometer to sample dissolved organics, a conductivity probe to measure salinity, and a Raman spectrometer to identify minerals on the lake bed. If there are active vents, hydrothermal-style plumes of warmer methane-carrying material from the subsurface, the sub would detect them as temperature and chemical anomalies. It could follow the gradient to the source. The mission would also test whether the lakes stratify, with heavier ethane settling in the depths and lighter methane floating on top. Cassini's radar couldn't resolve layers, but direct sampling could. If the bottom is ethane-rich, it means the lake is old, millions of years of evaporation and rain concentrating the heavier fraction. A submarine could search for chemical gradients that betray metabolic activity, but it could also discover something much stranger. The Tholin sludge at the bottom of Caspian Sea is exactly what scientists want to study, but it's also what makes landing there nearly impossible. Any probe heavy enough to carry instruments would punch through the liquid surface and sink straight into meters of tarry sediment, its communications antenna buried, its power systems choked. Engineers have proposed floating platforms instead, buoyant enough to rest on the ethane-methane mixture while deploying sensors into the liquid below. The density difference between the methane-rich surface and the ethane-rich depths means a carefully ballasted platform could stay afloat for years, drifting with the currents, mapping temperature and composition as it goes. But there's a problem. A floating platform rides on the surface, sometimes dipping a few meters down. The sediments, the layers of organic material deposited over millions of years, sit at the bottom, 300 meters below in Kraken's deepest basins. You can measure the liquid, map its chemistry, track its flow. You can't touch the archive. But a floating platform can't sample the sediments, and the sediments are where the oldest organic material is buried. A follow-on mission could solve this. Picture a floating platform, stable on the Methane Sea, carrying a coring drill. The drill descends through the liquid column, punches into the sediment, and extracts a cylindrical sample, 2 meters long, preserving every layer. Each centimeter represents thousands of years. The core would reveal Titan's climate history written in organic chemistry. Periods when the atmosphere was thicker would leave heavier deposits of Tholin rain. Periods when the lakes evaporated would concentrate ethane and leave gaps in the record. Isotopic ratios in the nitrogen and carbon would track how the atmosphere evolved, how much methane was lost to space, how much was replenished from below. And if something was living in those sediments, metabolizing, reproducing, dying, it would leave traces, lipid biomarkers, molecules with structures too specific to form abiotically. Isotopic fractionation, the signature of biology selecting lighter isotopes over heavier ones. Microfossils, if the preservation was perfect, cells mineralized in ethane ice. If those sediments contain isotopic anomalies or molecular fossils, they could prove life existed on Titan in the past, even if it doesn't today. Titan's year is 29.5 Earth years long. Each season lasts 7.5 years. Cassini arrived in 2004 during southern summer when the southern polar lakes were full and the northern plains were dry. By the time the mission ended in 2017, it was northern spring. The lakes had flipped. Caspian Sea, Ligeia Mare, Punga Mare, all of them filled as methane evaporated from the south and rained down in the north. Dragonfly will arrive in 2034 during northern summer. The lakes will be at their fullest. The atmospheric circulation will have reversed again, pumping methane toward the North Pole, feeding the hydrocarbon seas. Cassini saw the transition. Dragonfly will see the peak. But that timing is a gamble. Titan's seasons are predictable on average, but the storm systems aren't. The 2010 outburst, a massive methane storm that erupted near the equator, dumped rain across the tropics and temporarily refilled dry lake beds. It lasted weeks, then vanished. Cassini caught it by accident. But by the time Dragonfly lands, the climate may have already changed, and some lakes may have dried up entirely. Scientists ran the simulations forward. General circulation models for Titan predict that over the next century, the northern polar lakes will start to evaporate. At the same time, the empty southern basins will begin to refill. The cycle mirrors Earth's own Milankovitch oscillations, but compressed. Titan's seasons run on a 29.5-year loop, locked to Saturn's orbit around the Sun. But the models show something stranger beneath that rhythm. Long-term trends don't stabilize. The northern hemisphere has been wetter for thousands of years, possibly tens of thousands. Whether that reverses or continues, nobody knows. The uncertainty compounds. Small changes in albedo, in haze density, in methane release from the surface can tip the entire system. One model shows Ligeia Mare shrinking by 30% before 2100. Another shows it deepening. The range of outcomes is enormous, and the observational baseline is just 13 years. If Titan's climate is changing on timescales of decades, any life in the lakes would have to migrate or adapt. On Earth, organisms survive in boiling acid pools at Dallol. They thrive beneath the frozen surface of Antarctica's Lake Vostok, sealed under 4 kilometers of ice for 15 million years. Tube worms cluster around deep-sea vents at 400 degrees Celsius, metabolizing sulfur instead of oxygen. If life exists on Titan, it would need that same kind of biochemical flexibility. The lakes appear and vanish over centuries. Any organism would have to enter dormancy during dry periods, encased in some kind of protective cyst. Then, when the methane returns, it would need to reproduce rapidly before the next evaporation cycle. The analogues get stranger. Halophiles on Earth can tolerate salt concentrations that would kill most cells. Psychrophiles replicate at -15 degrees Celsius, their enzymes re-engineered to function in near-frozen water. Titan's organisms would need to operate in liquid methane at -179 degrees Celsius, a solvent with entirely different chemistry. But there's one Titan environment even more extreme than the lakes, the dunes. The dunes aren't sand. They're organic particles, each grain between 200 and 300 microns across. Cassini's radar mapped them across the equator, dark streaks that run for hundreds of kilometers. They're made of tholins, complex polymers produced when ultraviolet light breaks apart methane and nitrogen in the upper atmosphere. Those particles drift down over millions of years. They settle on the surface, get picked up by Titan's sluggish winds, and saltate across the landscape. The grains are eroded, transported, deposited in waves that mirror the dunes of the Namib Desert. But the composition is alien. Spectroscopy shows signatures of benzene, hydrogen cyanide, and long-chain hydrocarbons. Beneath the surface, radar suggests something else. Water ice clathrates, crystalline cages that trap methane and ethane molecules. The dunes may be layered, organic material on top, volatile rich ice below. If the temperature shifts even slightly, those clathrates destabilize and release their contents into the atmosphere. If the dunes contain clathrates, they're not just sand, they're a frozen methane reservoir that could feed the atmosphere for another billion years. Here's what makes that reservoir so nervous. At Titan's surface, roughly 94 Kelvin and about 1.5 times Earth's pressure, methane clathrates sit right at the edge of stability. They're a lattice of water ice caging methane molecules, and that cage only holds if the temperature and pressure stay in a narrow window. Nudge either one, and the whole structure can let go. A few degrees of seasonal warming near the equator, a slug of heat from below, or the shock of an impact, and the cage collapses. The trapped methane flashes out of the ice and rushes upward. When that happens on a large scale, it doesn't leak, it surges. A big enough release would pour methane into the sky faster than the atmosphere can process it, temporarily thickening the air and spiking the greenhouse effect across whole regions of the Moon. And Cassini may have witnessed exactly that event in 2010. In the middle of 2010, Cassini's instruments caught something odd over Titan's low latitudes. Methane concentration jumped, a sudden localized spike that didn't fit the slow, steady numbers the spacecraft had been logging for years. And it lined up with a massive storm system boiling up over the equatorial deserts. Those regions had been bone dry for the entire mission. Then, almost overnight, dark patches spread across roughly 500,000 square kilometers, the signature of methane rain hitting the surface. Something had loaded the atmosphere with fresh fuel, fast. Models point to two suspects, and both are unsettling. Either a clathrate deposit destabilized and vented its methane, or a subsurface reservoir cracked and breached upward through the crust. If clathrate outbursts are common, they could explain why Titan's atmosphere has survived for billions of years, but they also mean the methane supply is finite. And that supply is under constant attack from above. At the top of Titan's atmosphere, solar UV and the raw solar wind hammer the molecules, breaking methane and nitrogen apart and flinging the pieces into space. There's no strong magnetic field to shield the moon, so the erosion never stops. Cassini actually measured the bleed. Titan loses somewhere around 7 tons of hydrocarbons every single day, escaping off the top of the atmosphere and trailing into the darkness around Saturn, day after day, for billions of years. Do the arithmetic, and it turns grim. At that rate, Titan's atmosphere would vanish in 10 million years, unless something is replenishing it even faster than it's being lost. Not all of it escapes. Cassini's magnetospheric instruments traced a ring of neutral hydrogen and nitrogen atoms circling Saturn at exactly Titan's orbital distance. A torus, 2.4 million kilometers in circumference, fed by atmospheric loss. The particles drift through Saturn's magnetosphere, some getting ionized and swept away by the solar wind, others lingering for months before colliding back into Titan or spiraling into Saturn's atmosphere. It's a slow leak, constantly replenished, constantly draining. The density is vanishingly thin, about 50 atoms per cubic centimeter, but the total mass adds up. Over a Titan year, roughly 29 Earth years, the torus cycles through 10,000 metric tons of material. A river in space, invisible except to particle detectors. But the most surprising thing Cassini found wasn't what was leaving Titan, it was what was entering it. 1,200 kilometers away, Enceladus vents water vapor and organic molecules from geysers at its south pole. 200 kilograms per second, blasted into space at 400 meters per second. Cassini flew through the plumes in 2005 and tasted seawater. Most of it forms Saturn's E-ring, a diffuse band of ice grains, but some escapes the ring's gravitational pull and spreads outward through the system. Cassini's dust analyzer tracked particles all the way to Titan's orbit. The math is precise. Enceladus ejects roughly 6 million metric tons of water per year. About 0.3% of that reaches Titan, falling into the upper atmosphere as microscopic ice crystals that sublimate and mix with the nitrogen. If Enceladus is seeding Titan with water and organics, the two moons are chemically connected, and Enceladus's subsurface ocean could be influencing Titan's organic chemistry. Models published in 2018 estimated that 5 to 10% of the organic molecules in Titan's stratosphere originated at Enceladus. Methanol, ammonia, formaldehyde, traces of complex hydrocarbons, all synthesized in a subsurface ocean 500 kilometers away, then delivered by interplanetary drift. That creates a problem for Dragonfly. When it lands in 2034 and starts analyzing surface chemistry, how do you distinguish native organics from imports? A methane molecule formed in Titan's atmosphere looks identical to one carried in on Enceladus ice. The answer is contamination can't hide isotopes. If an organic came from Enceladus, its oxygen and hydrogen ratios will match seawater. If it formed on Titan, the nitrogen isotopes will match the atmosphere's distinctive enrichment pattern. But there's a way to tell the difference. By measuring the isotopic signatures of the nitrogen, Titan's N15 to N14 ratio is 1.5 times higher than Earth's and almost 4 times higher than what you'd expect from the solar nebula where Saturn formed. The heavier isotope has been enriched, concentrated over time. There are only 2 known processes that do this at planetary scale. The first is atmospheric escape. Lighter nitrogen-14 molecules move faster, so they're preferentially stripped away by solar wind and UV radiation. What's left behind gets progressively heavier. It's a slow fractionation that takes billions of years, and Titan's ratio fits the timeline almost perfectly. The second process is biological. Life on Earth preferentially uses nitrogen-14 because it's easier to incorporate into amino acids and DNA. When organisms die and decompose, the leftover nitrogen in the environment becomes enriched in nitrogen-15. The signature gets locked into sediments, into the atmosphere. No one's claiming Titan has biology based on this alone. The atmospheric escape model works without it. But the isotope ratio is consistent with both explanations, and you can't rule one out from orbit. If the nitrogen isotopes are a biosignature, they're the oldest one, because they've been accumulating for billions of years. Titan wasn't always like this. Computer models run the clock backward, stripping away methane layer by layer, and what you get 4 billion years ago is a moon with a thin nitrogen envelope and almost no haze. The orange shroud came later. Methane had to be added, either by cryovolcanoes venting it from the interior or by comet impacts delivering it from outside. Once it reached a critical threshold, photochemistry kicked in. Sunlight tore the methane apart, and the fragments reassembled into ethane, propane, benzene, and the aerosols that built the haze. But here's the problem. Methane gets destroyed faster than it gets replaced. Photolysis breaks it down in about 10 million years, which means Titan's current atmosphere can't be stable. It's either being actively resupplied right now, or we're seeing it in the middle of a transient event, a temporary window. Some models suggest Titan cycles between methane-rich and methane-poor states every few hundred million years, driven by cryovolcanic pulses or orbital shifts. If that's true, then the lakes are episodic. They fill, they evaporate, they vanish. If Titan's atmosphere is temporary, then so are the lakes, and any life that depends on them is living on borrowed time. Before Cassini arrived, the leading model predicted Titan would have a global ethane ocean hundreds of meters deep. The math was simple. Methane gets broken down by sunlight. Ethane is the stable product, and over 4 billion years, you accumulate enough to cover the entire moon. Cassini's radar painted a different picture. The seas cover less than 2% of the surface. They're mostly methane, not ethane, and the deepest one, Kraken Mare, is only about 160 meters at its maximum. The global ethane inventory is orders of magnitude lower than predicted. Some of it's in the lakes, dissolved. Some of it's in the atmosphere as vapor. Some of it probably soaked into the porous surface and froze into the crust. But even accounting for all of that, the numbers don't close. You're missing roughly 10 kilometers worth of liquid ethane spread across the entire moon. One hypothesis is that it reacted with surface minerals to form solid carbonates or clathrates, compounds that lock the ethane away underground. Another is that Titan's methane supply turned on recently, geologically speaking, so there simply hasn't been enough time to build up the ocean. Where did all the ethane go? The answer might be hiding underground. Radar data from Cassini suggests Titan's crust is porous, riddled with voids and fractures extending hundreds of meters down. Scientists think ethane and other liquid hydrocarbons could have soaked into that porous ice the way water fills an aquifer on Earth. They call it an alkanofer. Instead of groundwater, it's liquid ethane, propane, and butane saturating the subsurface like a sponge. Estimates suggest this hidden reservoir could hold more hydrocarbons than all the surface lakes and seas combined, trapped in pore spaces between ice grains. The radar reflectivity of certain plains regions matches what you'd expect from ice saturated with liquid organics. Those flat, dark expanses aren't just ancient lake beds. They might be sitting on top of a subsurface ocean of alkanes stretching for kilometers in every direction. If true, Titan isn't just geologically active on the surface. It's saturated with liquid hydrocarbons all the way down to the ice shell. But where does the methane keep coming from? One answer is cryovolcanism. Cassini spotted dozens of potential cryovolcanic features, domes, and calderas where water ice, mixed with ammonia, erupts from below. If those eruptions are pulling in surface organics, they're dragging them back into the warm interior. Down there, heat and pressure break complex hydrocarbons apart. Ethane, propane, and tholins decompose back into methane and hydrogen. That methane dissolves into subsurface water pockets, then gets vented back to the surface through cryovolcanic plumes. It's a feedback loop, surface to interior and back again. This would mean Titan's methane isn't primordial. It's being continuously recycled, processed through the moon's interior like a planetary distillery. The surface lakes feed the volcanoes feed the atmosphere, and the atmosphere rains back down into the lakes. But if the loop is closed, it should eventually run out of methane. And yet Cassini's final measurements suggested Titan is nowhere near that point. The numbers don't balance. Titan loses roughly 5 × 10^27 molecules of methane per second to photolysis in the upper atmosphere, broken apart by ultraviolet light. At that rate, the current atmospheric reservoir would be gone in 10 million years. That's a blink in geological time. The subsurface helps. If the alkanopher and clathrate deposits are real, they could hold enough methane to refill the atmosphere for another 100 million to 1 billion years, depending on the porosity and depth. Add in cryovolcanic recycling, and the timeline stretches further. But even 1 billion years isn't enough. Titan is 4 billion years old. If it's been losing methane this fast for most of its history, the subsurface reservoirs should be nearly exhausted by now. Yet the atmosphere is still thick, still stable, still replenishing itself. Something else is feeding the system. But there's a deeper reservoir no one expected, inside the rocky core itself. Cassini's gravity measurements revealed something unexpected. Titan's core isn't solid rock. It's a hybrid, a mixture of silicates and hydrated minerals, possibly laced with clathrates, cage-like structures that trap methane molecules inside mineral lattices. These clathrates could have formed during Titan's birth, when the moon was still hot and methane was being locked into the crystallizing rock. Over billions of years, tidal forces and radioactive decay could have destabilized those cages, releasing methane into fractures that snake upward through the mantle. The numbers are staggering. If even 1% of the core's methane is available for outgassing, that's enough to replenish the atmosphere for 4 billion years. The lakes, the rain, the rivers, all of it could be exhaust from a geological engine buried 2,500 kilometers below the surface. If the core is outgassing methane, Titan's atmosphere could be sustained for billions of years, long enough for life to originate, evolve, and spread. But the core isn't the only heat source. Titan orbits Saturn in an eccentric ellipse, stretching and compressing the moon with every pass. That flexing generates friction, and friction generates heat. Models estimate 1 to 2 gigawatts of tidal heating, roughly the output of a large nuclear power plant. It's not enough to melt the ice shell, but it's enough to keep the subsurface ocean liquid and maintain convection currents that transport methane upward through cracks and weak zones. The heat is uneven. Regions near the equator, where tidal strain peaks, could be warmer than the poles. That asymmetry might explain why some cryovolcanic features cluster along specific latitudes, and why Titan's surface deforms in ways that don't match a perfectly rigid shell. And in Cassini's final year, radar measurements revealed the ice shell is flexing more than models predicted. Cassini measured Titan's tidal bulge, the slight rise and fall of the surface as Saturn's gravity needs the moon. The amplitude was larger than expected, which means the ice shell is more elastic, more responsive to stress. Working backward from the deformation, scientists calculated the shell is 50 to 100 kilometers thick, thinner than early estimates of 150 kilometers. That puts the subsurface ocean within 50 kilometers of the surface in some regions, close enough that fractures could penetrate all the way down. A thinner shell fractures easier. It flexes, cracks, and opens conduits that allow pressurized fluids to ascend. Cryovolcanoes aren't random. They're pressure valves, weak points where the ocean finds a way through. If the shell is thin and fractured, cryovolcanic conduits could be actively pumping methane and organics to the surface right now. Cassini saw the evidence scattered across Titan's surface, radar hotspots that appeared and faded between flybys, transient infrared anomalies near suspected volcanic zones, isotopic signatures in atmospheric methane that matched cryovolcanic outgassing, not photochemical production. The methane replenishment rate is the smoking gun. Titan loses about 120 million kilograms of methane per year to photolysis, yet atmospheric levels stay constant. There's no reservoir of hydrocarbons on the surface large enough to explain it. The ocean has to be feeding the atmosphere, and cryovolcanoes are the delivery mechanism. But no mission has caught an eruption in progress. Cassini's 127 flybys caught Titan at snapshots, minutes out of decades. The hotspots could be cooling lava domes or active vents beneath haze. We've inferred activity from chemistry and geology, never watched it happen. Dragonfly's seismometers might detect a cryovolcanic event or even trigger one by landing near a fault zone. Titan's crust isn't static. If cryovolcanoes are active, the ice shell is fractured and pressurized, capable of sudden shifts. Dragonfly could land in a region where subsurface methane is venting through fissures, or where tidal stress is building toward a quake. Engineers designed the lander to target geologically stable terrain, flat interdune plains, and dried lakebeds. But Titan's surface changes. Cassini saw dune fields shift, shorelines recede, and bright features appear in infrared where none existed before. The safest landing zone today might fracture tomorrow. Ice quakes on Titan wouldn't feel like Earth's earthquakes. The crust is water ice at 94 K, brittle and rigid. A tidal fracture could snap open in seconds, releasing pressurized methane in a violent plume. Dragonfly's rotors give it mobility Earthlanders don't have, but escape windows are narrow. The mission timeline assumes 2 years of flight time, hopping between sites every 16 Earth days. Each landing is a calculated risk. The biggest surprise, though, would be finding life, and Dragonfly's instruments are designed to detect it. Dragonfly carries a mass spectrometer sensitive enough to identify individual organic molecules and measure their chirality. Life on Earth uses left-handed amino acids and right-handed sugars exclusively. Abiotic chemistry produces both in equal amounts. If Titan's organics show a chiral preference, that's a biosignature. The lander will also search for metabolic byproducts, fatty acids with even carbon chains, branched hydrocarbons, and nitrogen-rich compounds that match biological synthesis pathways. Isotopic ratios matter too. Biology fractionates isotopes predictably, favoring lighter isotopes in metabolic reactions. Carbon-12 over carbon-13, nitrogen-14 over nitrogen-15. Cassini found those isotopic anomalies in Titan's atmosphere, but couldn't pin them to biology. Photochemistry and cryovolcanic outgassing produce similar patterns. Dragonfly will sample surface material directly, drilling into organic-rich dunes and evaporite deposits where any microbial activity would concentrate. Detection of chiral asymmetry, metabolic lipids, or biogenic isotope ratios would be evidence of life. But proving life exists on Titan won't be straightforward. Because Titan's organics are so complex, distinguishing biology from chemistry is nearly impossible without a living sample. Dragonfly will be baked, irradiated, and wiped down with solvents before launch, following NASA's planetary protection protocols. But there's a hard limit to how clean you can make a spacecraft. Heat sterilization above 125 degrees Celsius would fry the flight computer, and UV lamps can't reach every crevice in the rotors or sample drill. Engineers estimate that even after aggressive cleaning, Dragonfly will carry somewhere between 300,000 and 500,000 bacterial spores on its surfaces. Most will die in the vacuum of space or Titan's frigid surface, but not all. Some extremophiles can survive years of dormancy in conditions far harsher than a spacecraft hull. The contamination budget is a calculated risk. Mission planners weigh the science return against the odds of accidentally seeding Titan with Earth biology. The math says it's acceptable, but acceptable doesn't mean zero. If Dragonfly finds life, scientists will have to prove it's native to Titan and not a stowaway from Earth. Lab tests show Earth microbes freeze solid within seconds in liquid methane at -179 degrees Celsius. Their cell membranes rupture, enzymes denature, and metabolic chemistry stops. Even hardy tardigrades can't survive prolonged exposure. That makes surface contamination unlikely, at least on timescales that matter for Dragonfly's 3-year mission. The real threat is subsurface. If a future lander drills through 50 kilometers of ice to sample the ocean directly, any surviving microbes could be delivered straight into liquid water at temperatures warm enough to support metabolism. Once inside, they'd face competition from native organisms, if any exist, or they'd find an empty niche and spread unchecked. The Outer Space Treaty requires nations to avoid harmful contamination of celestial bodies, but harmful is vague. Does contamination mean introducing viable organisms, or just altering the chemical environment? International committees have debated the wording for decades without consensus, but the reverse risk, bringing Titan life back to Earth, is even more controversial. A Titan sample return mission would require a lander, an ascent vehicle, an orbiter for rendezvous, and a re-entry capsule rated for hypersonic atmospheric speeds. Current estimates put the price tag at $40B to $60B, with a 20-year development timeline. That's more expensive than the Apollo program adjusted for inflation, and twice as long. The returned samples, frozen organic sludge sealed in titanium canisters, would never touch open air. They'd be transferred directly into a biosafety Level 4 containment lab, the same classification used for handling Ebola and Marburg virus. Technicians in positive pressure suits would analyze the material under triple-layered airlocks, incinerating any waste. The precautions aren't paranoia. In 1969, Apollo 11 astronauts spent 3 weeks in quarantine after returning from the Moon, even though scientists knew the odds of lunar pathogens were effectively zero. Titan's organics are far more complex, and its subsurface ocean could harbor active biology. If Titan life is biochemically incompatible with Earth life, the risk is minimal, but if it uses similar molecular machinery, it could be catastrophic. The biochemistry of any Titan organism would almost certainly be unrecognizable. Earth life uses water as a solvent, lipid bilayers for cell membranes, and ATP for energy transfer. Titan life might use liquid methane or ethane as a solvent, with membranes made of nitrogen-based compounds, stable at -179 degrees Celsius. Its energy sources could be equally alien. Instead of oxidizing glucose, it might reduce acetylene with hydrogen, a reaction that releases energy even in Titan's deep cold. The amino acids might be mirror images of ours, the nucleic acids, built on entirely different backbones. This radical incompatibility makes cross-contamination unlikely. A methane-based organism probably can't metabolize Earth's water-based biochemistry, and vice versa. But we've never tested life from two independent origins against each other. We don't know if some molecular interaction, some unanticipated pathway, could bridge the gap. The real question isn't whether Titan life is dangerous, it's whether finding it would change how we search for life everywhere else. For decades, the definition of habitable has been simple: liquid water, moderate temperatures, a source of energy. Titan meets none of these criteria. Its surface temperature is -179 degrees Celsius, cold enough to freeze carbon dioxide into dry ice. There's no liquid water anywhere near the surface, and no oxygen in the atmosphere. Yet it has lakes that fill and drain with the seasons. It has rain, rivers, and coastlines shaped by erosion. It has an atmosphere thicker than Earth's, a hydrological cycle, and organic molecules raining from the sky. It has, in other words, all the dynamic chemistry and energy flow we associate with habitability, just built from different materials. The European Space Agency's definition of a habitable zone is already outdated. It assumes rocky planets orbiting in a narrow band where water stays liquid. Titan sits 1.4 billion kilometers from the Sun, far beyond that zone, yet it may be more chemically active than Mars ever was. If life can emerge in liquid methane at -179 degrees Celsius, the number of habitable worlds in the galaxy just increased by orders of magnitude. As of early 2024, astronomers have confirmed over 5,500 exoplanets. Many are gas giants like Jupiter and Saturn, orbiting in the outer reaches of their star systems. And if our solar system is any guide, those giants likely host dozens of moons each. We can't detect exomoons yet. The signal is too faint, the wobble too subtle. But statistical models suggest there could be trillions of large moons in the Milky Way alone. If even a fraction resemble Titan, with thick atmospheres, subsurface oceans, and active organic chemistry, then moons may vastly outnumber habitable planets. The implications are staggering. We've spent 30 years cataloging rocky worlds in the habitable zones of stars, refining our models of where liquid water can exist on a planetary surface. But life might not need a star's warmth at all. It might thrive on tidal heating, locked in orbit around a giant planet, shielded from radiation by a magnetosphere it borrows from its host. And that raises a disturbing possibility. We may have been looking in the wrong places for decades. Back in 1961, Frank Drake scribbled an equation on a chalkboard to guess how many communicating civilizations might share our galaxy. It multiplies things like how many stars form, how many have planets, and how many of those planets ever spark life. Plug in confident numbers and you get thousands. Plug in cautious ones and you get exactly one, us. But every version of that equation carries a hidden assumption baked into the fine print. It assumes life looks roughly like ours, carbon chemistry swimming in liquid water at temperatures a human would find comfortable. Titan breaks that assumption wide open. If methane can host biology at -179 degrees Celsius, then the fraction of worlds capable of life just jumped, and every estimate that came before was too small. Widen the definition and the galaxy suddenly looks crowded. But there's a catch that cuts the other way. A living world we can't recognize counts for nothing in our tally, because we'd walk right past it. If Titan life exists, but is chemically invisible to our instruments, we need to rethink what biosignatures we're searching for on other worlds. Everything organic we've found on Titan is still built on carbon, the same versatile atom that assembles every living thing on Earth. But carbon isn't the only element that bonds in long, complex chains. Silicon sits right below it on the periodic table and shares many of the same tricks, and at Titan's brutal cold, those silicon structures could hold together instead of falling apart the way they do in Earth's heat. Then there's nitrogen, abundant in Titan's air and its lakes, capable of forming rings and chains that chemists have sketched only on paper. Imagine a cell that uses liquid methane the way we use water, its membranes stitched from molecules that would dissolve instantly in your bloodstream. We have no proof any of this walks or breathes on Titan. We only know the chemistry isn't forbidden. That's the quiet thrill of it. Future missions might need to hunt for signals we haven't even thought to name, patterns of organization rather than familiar molecules. But the most radical implication is philosophical, not scientific. Ever since Copernicus pushed Earth out of the center of the solar system, science has kept repeating one uncomfortable lesson. We are not special. Our star is ordinary, our galaxy is one of trillions, and our chemistry may be one option among many. The principle says, whenever we assume we're the exception, we're usually wrong. Now apply that to life itself. If a frozen moon locked around a gas giant, drenched in radiation and starved of sunlight, can still brew biology from methane and cold, then life stops looking like a miracle. It starts looking like something chemistry does whenever it gets the chance. Not a lucky accident, but an expected result, given enough time and the right ingredients. Follow that thought and it turns cold. A universe where life springs up easily should be teeming. Every promising world a candidate, every quiet lake a possible cradle. The galaxy has had billions of years and hundreds of billions of stars to work with. And if life is inevitable, the absence of detectable civilizations in the galaxy becomes even more puzzling. That's the Fermi paradox in its starkest form. Enrico Fermi asked the question in 1950 over lunch at Los Alamos. If intelligent life is common, where is everybody? We've scanned thousands of stars for radio signals, analyzed atmospheric spectra for industrial pollutants, searched for megastructures that could harvest stellar energy. Nothing. Titan doesn't resolve the paradox, but it sharpens it. If hydrocarbon lakes can support biochemistry, if methane rain can sustain metabolic cycles, then habitable environments aren't rare exceptions. They're variations on a theme. Life might be common while remaining microbial, locked in place by gravity wells and atmospheric chemistry, never developing technology or language or curiosity. The silence could mean we're genuinely alone in an improbable universe. It could mean intelligence is the rarest outcome, that cognition requires such a specific evolutionary path that it's happened once in 13.8 billion years. Or it suggests something darker, that civilizations arise and vanish long before they can communicate across interstellar distances. The Great Filter is the evolutionary choke point that stops life from spreading across the galaxy. It could be behind us, the improbable jump from chemistry to self-replication, the leap from prokaryotes to eukaryotes, the invention of multicellular complexity. If so, we've already passed the hardest test, and the cosmos is ours to inherit. Or the filter lies ahead. Nuclear war, runaway climate change, artificial intelligence we can't control, bioengineered pandemics. The same cognitive abilities that let us build spacecraft also let us design our own extinction. Every silent star system could be a civilization that didn't make it, a world that burned bright for 10,000 years and left no trace. Finding microbes on Titan would tell us which scenario we're living in. If life starts easily wherever conditions allow, then the galaxy should be full of biospheres, and the filter must come later. Earth's history becomes a warning, not an exception. Every step we take into space carries the weight of knowing that something stops almost everyone. But Cassini's final discovery wasn't about the future, it was about Titan's past. Radar topography from the final flybys revealed something unexpected. Ancient shorelines far from the current lakes, erosion patterns that match large standing bodies of liquid, sediment layers that suggest Titan's seas once ran much deeper, climate models reconstructing the Moon's thermal history point to an epoch 3 to 4 billion years ago when the atmosphere was denser and the surface warmer. The young sun was fainter then, but Saturn's tidal heating and a thicker greenhouse blanket could have kept Titan's surface above 90 K instead of the current 94 K. That's enough for liquid ethane to dominate over methane, for seasonal cycles to drive more vigorous evaporation, for seas to cover 40% of the surface instead of 2%. Radar reflectivity measurements show subsurface layers consistent with ancient seafloor deposits now buried under dunes. Those vanished oceans would have been planetary-scale laboratories, mixing organics over millions of square kilometers, concentrating reactants in tidal pools, cycling through freeze-thaw transitions that could drive molecular complexity. The chemistry that struggles in Ligeia Mare today might have thrived in a younger, wetter Titan. If Titan had a warmer, wetter past, it may have been even more habitable then than it is now. The models tell a story of a different world. 4 billion years ago, Titan's interior was hot. Radioactive potassium-40 and thorium were still decaying at full intensity, pumping heat into the ice shell. Saturn's tidal forces were stronger then, kneading Titan's interior like dough, generating friction heat that kept the subsurface ocean liquid and thick. That heat leaked upward. Atmospheric models suggest surface temperatures could have climbed to 94 K, maybe higher. That's above methane's triple point of 90.7 K. For the first time, Liquid methane lakes weren't just thermodynamically possible. They were stable, widespread, persistent. Rain fell, rivers carved valleys, shorelines stretched across latitudes. The atmosphere itself was denser, maybe 2 or 3 times today's pressure, trapping more greenhouse heat in a feedback loop. Photochemistry was running faster, churning out organics at rates we can only estimate. If there was ever a window for chemistry to cross into biology, this was it. A warm Titan, wet and organic rich, under a thick haze that filtered UV but let visible light through. But that epoch didn't last. Radioactive isotopes decayed. Tidal heating weakened as Titan's orbit circularized, the atmosphere thinned. Surface temperatures dropped back below 90 K, and the methane lakes began to freeze or evaporate. If life originated during that warm epoch, it may have since retreated underground or gone extinct. Titan's climate history isn't a smooth curve, it's a series of collapses. Every few 100 million years, orbital perturbations shift the balance. Nitrogen condenses out of the atmosphere in polar cold traps. Pressure drops. Lakes evaporate into the thinning air, and the methane cycle stalls. Then the pendulum swings back. Volatile reservoirs buried in the crust outgas. The atmosphere rebuilds over 10 or 20 million years, and the rains return. But each cycle resets the surface. Any organisms adapted to liquid methane would suffocate during atmospheric collapse. Any microbial mats clinging to shorelines would freeze solid when the lakes disappeared. We're seeing evidence of at least 3 major climate shifts in the geologic record. Cratering patterns suggest periods when erosion stopped completely, lakes vanished, and the surface froze under a thin nitrogen shroud. Then layers of fluvial channels cutting through older terrain, marking the return of liquid. Each transition is an extinction filter. Surface life on Titan would have faced repeated apocalypses, each one wiping the slate nearly clean. But subsurface life in the ocean would be insulated from those changes and could have survived for billions of years. On Earth, we've found microbial life 5 kilometers below the surface in South African gold mines. Bacteria living in fractured basalt beneath the seafloor, metabolizing hydrogen from serpentinization reactions. Archaea in aquifers under the Atacama Desert, untouched by sunlight for millions of years. Life doesn't need the surface. Titan's subsurface ocean sits 50 to 80 kilometers down, beneath an ice shell that acts as armor. Surface temperature swings, atmospheric collapse, methane lake evaporation. None of it penetrates that deep. The ocean temperature is locked near 270 K by the pressure melting point of ammonia water ice. Stable, dark, isolated. If serpentinization is happening at the rocky core interface, it's generating hydrogen gas. That hydrogen diffuses upward into the ocean, providing a continuous energy source independent of sunlight or surface chemistry. Microbes could be metabolizing that hydrogen right now, clustered around hydrothermal seeps, building a biosphere we have no way to image. The ocean has been there for 4 billion years, long enough for chemistry to explore every stable configuration, long enough for selection pressure to refine whatever works, long enough for an entire tree of life to diverge in complete darkness, never touching the atmosphere, never leaving a biosignature we'd recognize from orbit. If that biosphere exists, it's the most isolated ecosystem in the solar system and the hardest to reach. So, how do you reach it? The engineering challenge is extreme. You need a probe that can melt through 50 to 100 kilometers of ice, survive temperatures near 94 K, maintain communication through the ice shell, and carry instruments sensitive enough to detect biosignatures in a lightless ocean. The technology doesn't exist yet. NASA and ESA are testing cryobot prototypes on Earth's glaciers, autonomous nuclear-powered vehicles that melt their way downward, trailing fiber optic cables for data relay. The best terrestrial tests have reached depths of only 1.4 kilometers in Antarctic ice. Scaling that to Titan means a probe massing several tons, powered by a radioisotope heater that can run for years, navigating through ice that might contain pockets of liquid, fractures, or subsurface voids. Mission designers estimate 15 to 20 years of transit time through the ice alone. Deployment on Titan is at least 30 years away, likely longer. The earliest conceptual timeline puts a cryobot mission launch in the 2050s. And even if we reach the ocean, we might not recognize what we find. There's a hypothesis in astrobiology called the shadow biosphere. It suggests life could exist on Earth right now using biochemistry so fundamentally different from ours. Different solvents, different informational polymers, different metabolic pathways, that we've never detected it because we weren't looking for it. Our instruments are calibrated to find DNA, RNA, proteins, lipids. If something else is alive using arsenic instead of phosphorus, or silicon instead of carbon, or storing information in a molecule we've never seen, it would be invisible to standard biosignature detection. We'd sample it, analyze it, and classify it as abiotic chemistry. Titan could harbor exactly that kind of shadow biosphere. Life in the methane lakes might use entirely non-terrestrial biochemistry. Life in the subsurface ocean might mimic Earth's microbiology closely enough to recognize, or it might not. The more alien the biochemistry, the harder it is to design instruments that can detect it. You can't search for something if you don't know what signature it leaves. But the most profound mystery isn't whether life exists on Titan, it's the anomaly Cassini detected in its final orbits. In 2017, during Cassini's final polar passes, the visual and infrared mapping spectrometer picked up something strange, an unexplained spectroscopic signature in the haze layer above the North Pole, a narrow absorption feature at 3.4 micrometers that doesn't match any known organic molecule in Titan's atmosphere. The team checked it against tholins, nitriles, polycyclic aromatic hydrocarbons, benzene derivatives, every candidate compound in the chemical inventory. Nothing fit. The absorption depth was too sharp, the wavelength position slightly offset from anything in the lab database. It wasn't an instrumental artifact. VIMS had been calibrated extensively, and the same feature showed up in 4 separate flybys between April and September 2017. It only appeared when the North Pole was in summer, when convection was strongest and fresh material was being lofted into the stratosphere. By the time Cassini made its final plunge into Saturn's atmosphere, the feature had faded. The signature was faint, transient, and only appeared during certain atmospheric conditions, but it was reproducible across multiple flybys. So teams tried to recreate it in the lab. They simulated Titan's atmospheric chemistry, bombarded organic mixtures with UV light, generated aerosols at cryogenic temperatures. Nothing matched. The spectroscopic signature didn't correspond to any known molecule or aerosol structure. One hypothesis, a photochemical reaction that only occurs under Titan's exact combination of pressure, temperature, and UV flux, something so specific it can't be replicated on Earth. Another, an exotic aerosol geometry, maybe hollow spheres or fractal aggregates, that scatters light in unexpected ways. A third idea involves metastable molecules, compounds that exist briefly in an excited state before decaying into something else. By the time you capture them, they've already changed. You're not detecting the molecule itself, just its ghost. But none of these explanations fully account for the pattern Cassini recorded. One fringe hypothesis suggests the signature is biological, a metabolic byproduct of airborne microbes living in the haze. On Earth, microbes live in clouds. They've been found at altitudes above 10 kilometers, suspended in water droplets, metabolizing organic compounds carried up from the surface. Titan's haze is far thicker, full of complex organics, and protected from hard UV by methane and nitrogen absorption in the upper stratosphere. If organisms could harvest energy from photochemistry, breaking down tholins, oxidizing methane, anything that releases electrons, they could stay aloft indefinitely. No need for a surface, no need for liquid water, just a stable niche in the middle atmosphere where temperatures hover around 70 K and organic molecules rain down constantly. The haze itself could act as a scaffold. Aerosol particles are sticky, aggregating into chains and clusters. Microbes could cling to them, forming colonies that drift through the nitrogen sky. They'd be tiny, metabolically slow, but persistent, life adapted to a permanent float. But detecting airborne life would require a mission designed specifically to sample the haze, and no such mission is planned. The concept is straightforward. A hot air balloon filled with helium or heated nitrogen dropped into Titan's atmosphere during descent. It would drift at an altitude of 10 to 20 kilometers, right in the middle of the haze layer, for weeks or months. Onboard instruments would collect aerosol samples, analyze their composition with a mass spectrometer, search for isotopic signatures of metabolism. You'd look for chiral molecules, amino acids with a handedness bias, the kind biology produces. You'd measure carbon and nitrogen isotope ratios, check for depletions that suggest selective uptake. You'd image the aerosols at nanometer resolution, searching for structure that can't be explained by simple aggregation. A mission like this was proposed in 2017 for NASA's New Frontiers program. It didn't get selected. Budget constraints, competing priorities, the usual reasons. But the science case remains strong. If the North Polar anomaly is real, and if it's biological, a balloon mission is the only way to know. But even if the anomaly is just chemistry, it reveals how little we understand about Titan's atmosphere. So where does that leave us? After 13 years orbiting Saturn, after 127 flybys, after radar maps and spectrometry and infrared imaging, we still don't know what's replenishing Titan's methane. The atmosphere should have been stripped away in 10 million years, yet here it is, thick and hazy, with lakes full of the stuff. We don't know if the cryovolcanoes are active, or if Sotra Patera erupted yesterday or a billion years ago. We don't know if there's life in the lakes, something swimming beneath the ethane, or if the subsurface ocean harbors organisms we can't even imagine. We don't know what caused the magic island to appear and vanish, or if it'll show up again tomorrow. We don't know what the North Polar anomaly is, whether it's biology or photochemistry or something we haven't thought of yet. Every answer Cassini gave us opened 3 new doors. Every measurement revealed how much we'd been guessing. Cassini answered 1,000 questions about Titan, but raised 1,000 more. On September 15, 2017, Cassini fired its thrusters one last time and dove into Saturn's atmosphere at 77,000 miles per hour. The spacecraft had run low on fuel, and NASA faced a choice: let it drift, inert and uncontrolled, or destroy it deliberately. They chose destruction to protect Titan and Enceladus from contamination. As Cassini descended, it became the first spacecraft to sample Saturn's atmosphere directly. Its instruments measured atmospheric composition, pressure gradients, temperature profiles. The data streamed back to Earth in real time, transmitted at 84,000 bits per second across 1.5 billion kilometers of space. Then the signal stuttered. The spacecraft began to tumble as atmospheric drag overwhelmed its thrusters. Engineers on the ground watched the telemetry drop, bit by bit, until the carrier wave flatlined at 7:55 a.m. Eastern. Cassini had vaporized 1,900 kilometers above Saturn's cloud tops. Its atoms, now part of the planet it spent 13 years studying. The mission ended, but the data is still being analyzed, and new discoveries are still being published. Cassini returned 635 GB of raw data during its mission, stored across hundreds of thousands of individual files. That's 453,048 images, 3,650 gigabits of radar soundings, millions of spectrometry readings. When the spacecraft died, the real work had barely started. It takes years to process that volume. A single radar map requires cross-referencing dozens of passes, correcting for orbital drift and signal noise. Spectrometry data needs calibration against laboratory standards that didn't exist when the mission launched. In 2019, researchers reprocessed old infrared images and found seasonal haze patterns no one noticed in 2007. In 2021, a new analysis of gravity data revealed the ocean's depth more precisely. Every algorithm improves the archive. Machine learning tools trained on Earth data now scan Cassini images for features human eyes missed. The full picture of Titan is still emerging from measurements taken a decade ago, and scientists estimate it'll take another 20 years to extract everything the data contains. And that archive contains one final puzzle no one has solved. In April 2019, a team at Cornell running anomaly detection algorithms on Cassini's final descent telemetry flagged something strange. Buried in the carrier wave noise was a 0.7-second pattern that repeated 3 times over the last 83 seconds of transmission. The intervals weren't perfectly regular, but they were close. 11.4 seconds, then 11.9, then 11.2. Random noise doesn't cluster like that. The team ran the signal through every filter they had. It wasn't data corruption, wasn't a known spacecraft systems artifact, wasn't interference from the Deep Space Network receivers. The pattern sat at 8.4 GHz, right in the middle of Cassini's X-band downlink frequency. They published a technical note in IEEE Transactions on Aerospace and Electronic Systems, asking if anyone recognized the signature. No one did. The signal was too short to decode, too faint to trace, too regular to dismiss. It appeared nowhere else in 13 years of Cassini data. Some think it's an instrumental artifact. Others think it's a natural radio emission from Titan's magnetosphere. A few think it's something else. Titan is loud in the radio spectrum. Lightning in its methane storms generates bursts at frequencies between 1 and 16 MHz. Saturn's rotating magnetosphere sweeps across Titan every 10.7 hours, triggering Whistler mode emissions in the ionosphere. Cassini's radio and plasma wave science instrument catalogued 847 discrete natural radio events during the mission. Researchers cross-referenced every known emission type with the April 2019 signal. Lightning bursts are broadband and irregular. Magnetospheric interactions produce kilometric radiation at much lower frequencies. Ionospheric hiss is continuous, not pulsed. None of the signatures matched. The 8.4 GHz carrier frequency is particularly strange. Natural emissions from Titan peak below 20 MHz. At X-band, the Moon's atmosphere is nearly radio-transparent. If the signal originated from Titan, it would have to be generated by a mechanism no one has observed before. If the signal isn't natural and isn't instrumental, the only remaining explanation is contamination from an Earth-based transmission, but no matching transmission has been found. In February 2020, a preprint appeared on the archive server with a title that made headlines: Anomalous Structured Emission During Cassini's Final Titan Flyby, a Techno-Signature Candidate. The lead author, a postdoc at Caltech, argued the signal's regularity and frequency placement were inconsistent with known natural or human sources. The backlash was immediate. SETI researchers pointed out the sample size was too small, the signal-to-noise ratio too marginal, the analysis too speculative. Within 72 hours, 11 senior scientists had published rebuttals. The journal the paper was submitted to rejected it without peer review. The lead author retracted it 9 days later and left academia 6 months after that. But retracting the paper didn't erase the signal. It's still there in the raw telemetry files, archived at NASA's Planetary Data System. 3 independent teams have confirmed the pattern exists. No one has explained what generated it. The topic is now considered too controversial to publish on, so most researchers avoid it entirely. The scientific consensus is that the signal is an artifact, but no one has definitively proven what caused it. In 2019, a team at Cornell reanalyzed the signal using updated ionospheric models. They concluded it matched a resonance pattern from Titan's upper atmosphere during a solar flare event. Case closed, they said. 6 months later, researchers at ESA published a counter-analysis. They'd found the same signature in Cassini telemetry from 3 other flybys, none during solar activity. Their conclusion: spacecraft interference from the radio science subsystem, possibly a ground-based contamination in the original transmission. But a third team at Caltech noticed something both groups missed. The signal's frequency drift matched neither the Cornell ionosphere model nor the ESA interference pattern. It was 0.7 Hz off in both cases. Not much, but enough to matter. The debate hasn't been settled because no one can replicate the conditions of that flyby. Cassini's gone, and the geometry of that particular pass, 1,200 kilometers altitude at 34 degrees north latitude during Titan's northern winter, won't occur again until 2041. Whatever the signal is, it's a reminder that Titan still holds secrets we haven't even begun to understand. Dragonfly launches in 2028 and arrives in 2034. By then, the scientists who were undergrads when Cassini arrived at Saturn will be leading the mission. They grew up with those orange haze images as desktop wallpapers, studied Huygens data in grad school, and built careers around a world they've never touched. The mission timeline spans 2.7 years of surface operations, 8 landing sites, and 175 kilometers of total flight distance. Dragonfly will carry a mass spectrometer 100 times more sensitive than Cassini's, a seismometer to listen for cryovolcanic tremors, and gamma-ray sensors to map subsurface water ice. It'll touch down in the Shangri-La dune fields, the same region Huygens photographed in 2005. Except this time, we're not landing blind. We've mapped the wind patterns, modeled the atmospheric chemistry, and identified 23 specific targets where organics have accumulated in crater floors. Titan's no longer the orange mystery it was in 1980. It's a frontier now, with coordinates and geology and weather forecasts. But frontiers have a way of surprising us. Cassini was built by 260 scientists from 17 countries over 15 years. The spacecraft carried instruments designed in the 1980s that were still returning data in 2017. Engineers who worked on the original proposal retired before the mission ended, and their students became the mission's final operators. Every discovery came from someone noticing something unexpected in the data. The lakes were found because a radar technician saw dark patches that shouldn't have been there. The methane cycle was confirmed because an atmospheric modeler recognized a cloud formation from their simulations. The subsurface ocean was inferred because a geodesist measured Titan's shape to within 15 meters and realized it was wobbling. The mission succeeded not because of the technology, though the technology was extraordinary. It succeeded because people from different fields, different countries, different generations kept asking what they were looking at and refused to accept easy answers. Right now, there are 16 petabytes of Cassini data archived at NASA's Planetary Data System. Most of it has never been fully analyzed. Graduate students are still finding new moons, new ring structures, new chemical signatures in spectra that were recorded a decade ago. And the biggest discovery of all may still be waiting, not in the data we have, but in the data we'll collect next. So what's the plan? Dragonfly launches in 2028, arrives in 2034. It'll spend 2.7 years hopping across Titan's surface, sampling organics at impact craters, dune fields, and the margins of ancient lake beds. If it confirms prebiotic chemistry, the next step is a lake lander. That mission is penciled in for the 2040s. It would splash down in Kraken Mare, deploy a submersible, and analyze liquid samples for dissolved organics, polymers, maybe even membrane-like structures. The ice-penetrating mission comes after that, targeting the subsurface ocean in the 2050s. Each mission builds on the last. Dragonfly maps the chemistry. The lander tests the habitability of the surface seas. The ice probe goes deep, searching for hydrothermal vents and the kind of liquid water environment where Earth-like life could thrive. It's a 30-year roadmap, step by step, narrowing the search. But the timeline assumes funding, political will, and technological progress, none of which are guaranteed. NASA's planetary science budget is roughly $3.02 per year, and it has to cover everything. Mars sample return alone is projected at $11. Europa Clipper cost $5. A Uranus orbiter is being considered for the next decadal survey, and that's another $4 minimum. Titan missions are expensive. Dragonfly's price tag is $3.35, and that's just to get a rotorcraft there. A lake lander would cost more. An ice-penetrating submarine with a drill rig, power source, and comms relay, you're looking at $6 to $8, spread over 15 years of development. Every mission that flies means another mission delayed or cancelled. The Mars sample return overrun has already pushed back other flagships. When budgets tighten, the safe bet wins, and the safe bet is always Mars. Titan is the higher risk, higher reward option, and that makes it vulnerable. If Dragonfly finds definitive evidence of life, funding will flood in, but if it finds nothing, Titan exploration could stall for decades. Mars gets the majority of NASA's planetary science budget because it's closer, cheaper, and more familiar. A round trip takes 18 months instead of 7 years. Launch windows open every 26 months instead of once every 16 years. You can land a rover for $2.05 and get results within a decade. Titan is harder. The distance alone adds $1 in propulsion and power. The cold atmosphere requires radioisotope heaters. The low light levels mean solar panels are useless. Communication lag is 80 minutes one way, so every command sequence has to be autonomous. And you're working blind, testing hardware for an environment no Earth lab can fully replicate. But Mars is a dead world. Its atmosphere is thin, its water is frozen, and its surface is bathed in radiation. Titan has active chemistry, stable liquids, and a thick atmosphere that shields the surface. If you're looking for life, or the conditions that lead to life, Titan is the more scientifically rewarding target. The question isn't which world deserves more attention, it's whether we can afford to explore both. NASA can't do it alone. A mission capable of landing on Titan, surviving the cold, and analyzing the surface chemistry would cost upwards of $2 billion. That's why future proposals hinge on partnerships. ESA contributed the Huygens lander to Cassini. JAXA has proposed joint ice-penetrating radar systems. The model works. Cassini-Huygens returned 635 gigabytes of data over 13 years because two agencies split the cost and risk. But geopolitics shifts faster than mission timelines. A probe designed in 2025 won't launch until 2035 and won't arrive until 2050. That's 3 decades for treaties to fracture, budgets to collapse, partnerships to dissolve. China's space program is accelerating. Russia's relationship with the West has frozen. India's launching interplanetary missions at a fraction of traditional costs. The next Titan mission will need contributions from nations that may not be allies by the time the spacecraft reaches orbit. The search for life transcends politics, but the funding for that search doesn't. SpaceX reduced the cost of reaching low Earth orbit by 90%. Starship, if it succeeds, could cut deep space launch costs by another order of magnitude. That changes the math. A Titan submarine mission that once required $3 billion in government funding might drop to $800 million with commercial launch and private R&D. Blue Origin's in-space manufacturing, Rocket Lab's interplanetary smallsat buses, Axiom's private space stations. The infrastructure's assembling faster than the agencies anticipated. Private companies don't move at the pace of congressional budget cycles. They move at the pace of investor impatience and CEO ambition. But private funding answers to quarterly returns, not peer review. A NASA mission publishes every data set. A private mission might not. The science gets paywalled, the samples get patented, the discoveries get leveraged for intellectual property. Elon Musk's openly stated he wants to make life multiplanetary. Jeff Bezos wants to move heavy industry off Earth. If a billionaire decides Titan is worth exploring, the timeline could accelerate, but science-driven exploration could become profit-driven exploitation. Titan's surface has never been touched by Earth biology. Every probe we send carries microbial hitchhikers. Cassini was sterilized, but sterilization isn't perfect. Huygens landed, transmitted for 90 minutes, then went silent. It's still there, a metal capsule leaking trace organics into the methane-soaked regolith. Planetary protection protocols exist. NASA's Office of Planetary Protection sets contamination limits for missions to worlds that might harbor life. But the rules are recommendations, not enforceable law. No international treaty governs what happens when a private lander crashes into Ligeia Mare or a drilling probe punctures a subsurface reservoir. If Titan has life, it evolved in isolation for 4 billion years. It might use different amino acids, different solvents, different chemical logic. Introducing Earth microbes could be catastrophic, not because they'd thrive, but because they'd contaminate the one place in the solar system where we could study an independent origin. The question isn't just whether we can explore Titan, it's whether we should. And if we do find life, the next question is even harder. What do we do with it? There's a hypothesis in astrobiology called the zoo hypothesis. It suggests that advanced civilizations might know we're here, but they're deliberately keeping their distance. Like researchers observing animals in the wild, they let us evolve without interference. If that's true, then how we handle Titan could be our first test. Do we contaminate it with Earth microbes? Do we extract resources without understanding the ecosystem? Or do we study it carefully, respecting whatever might be there? Some scientists argue that our approach to Titan will signal what kind of civilization we are, whether we're ready to join a galactic community, or whether we're still too reckless, too short-sighted. It's not just about finding life, it's about proving we can be trusted with it. But the hypothesis assumes someone is watching, and we have no evidence of that. The alternative is harder to accept. If Titan is lifeless, and Mars is lifeless, and Europa turns out empty too, we might be alone in the solar system. Not just rare, alone. Earth's biosphere took 3.8 billion years to produce a species capable of building telescopes and spacecraft. That timeline required liquid water, a magnetic field, a stable orbit, and a moon to stabilize the tilt. The odds of that combination happening twice, even in 8 planets and 200+ moons, start to look vanishingly small. If we search Titan's lakes, drill through Europa's ice, and analyze Mars's ancient riverbeds and find nothing, the conclusion is unavoidable. Life on Earth wasn't inevitable. It was a statistical fluke, a one-time event in a system that's been churning for 4.6 billion years. But finding even one microbe on Titan would prove the opposite, that life is common, resilient, and inevitable. Titan orbits Saturn every 16 days. Saturn orbits the Sun every 29 years. The Sun orbits the Milky Way's center once every 230 million years, dragging the entire solar system through interstellar space at 828,000 kilometers per hour. From that perspective, Titan's methane lakes are temporary. They've existed for maybe 1 billion years out of a 4.5 billion year history. In another billion years, the Sun will brighten, Saturn's orbit will shift, and Titan's surface will change completely. Any life there now is living in a narrow window. The same is true for Earth. Our atmosphere has only had breathable oxygen for 2.4 billion years. Complex life has existed for 600 million, humans for 300,000. Cassini flew for 13. We're a species that's been technologically capable of interplanetary exploration for less than 70 years, and we're already imaging alien lakes in real time. And yet, in this fleeting moment, we have the technology to reach it and the curiosity to explore it. Titan isn't just another moon. It's the only place in the solar system with stable surface liquids besides Earth, the only world with a thick nitrogen atmosphere like ours, and the only laboratory where we can study prebiotic chemistry in real time. The organic molecules raining down from its atmosphere right now are similar to the ones that existed on early Earth 4 billion years ago. Every methane lake, every dune field, every cryovolcano is a natural experiment we can't replicate in any lab. If life can emerge from chemistry alone, without sunlight, without water, without everything we thought was required, Titan is where we'll find the evidence. If it can't, that's equally important. It tells us Earth might genuinely be special. The cost of a single Titan mission is $3.35 billion. The cost of never knowing is incalculable. We have the spacecraft, the instruments, the flight path already planned. Dragonfly will launch in 2028. The technology exists right now to answer a question humans have asked for millennia. If we don't search, we'll never know, and the question of whether we're alone will remain unanswered. Remember that bright spot in the Cassini image, the one that appeared where nothing should exist? Scientists eventually identified it as a transient cloud formation, methane ice crystals condensing in Titan's upper atmosphere and catching the sunlight at just the right angle. It appeared in July 2004, then vanished 10 hours later. Case closed. Except the bigger mystery was never that one anomaly. It's the methane itself. Titan's atmosphere should have been stripped away by solar radiation 10 million years ago. Something is replenishing it, continuously, on geological timescales. We don't know what. Internal reservoirs? Cryovolcanism? Subsurface chemistry we haven't imagined yet? And beneath that puzzle sits the deeper one. Those organic molecules covering every surface, those methane lakes cycling through seasons, that entire hydrocarbon system operating at 94K. We've catalogued the chemistry. We've mapped the terrain. We've confirmed the liquids. But we haven't answered the question that sent Cassini there in the first place. Dragonfly will arrive in a decade. Until then, Titan's secrets are safe. Titan changed what we search for. Before Cassini, astrobiology meant finding another Earth, a rocky planet in the habitable zone with liquid water and an oxygen atmosphere. Now we know life's possibilities are wider. Subsurface oceans, methane lakes, chemistry powered by tidal heating instead of sunlight. Every mission to Titan rewrites the definition. If Dragonfly finds biosignatures in those organic deposits, it won't just confirm life exists elsewhere. It'll prove life emerges wherever chemistry permits, that the universe might be full of worlds we'd never have thought to search. If it finds nothing, that's data too. It means Earth's combination of factors, whatever they are, might be rarer than we hoped. The radar data from Cassini's T-41 flyby in December 2007 showed something unexpected. A bright feature appeared in Ligeia Mare that wasn't there in earlier passes. By 2013, it had vanished. Then, in 2014, it reappeared 15 miles from its original position. The feature measured roughly 12 miles across and changed shape between observations. Scientists called it the Magic Island, but the name hides genuine confusion. Floating solids, bubbles, suspended organics, waves, none of the models fit perfectly. The subsurface ocean sits about 35 to 50 miles below Titan's icy shell, confirmed by gravity measurements during close flybys. It's probably salty, maybe rich in ammonia, to stay liquid at temperatures around -100 degrees Fahrenheit. The shell itself flexes with Saturn's tides, rising and falling by up to 30 feet. That flexing generates heat through friction, the same process that powers Enceladus's geysers. On Titan, the heat might be enough to melt pockets in the ice shell, creating temporary chambers where water and organics mix. If cryovolcanoes exist, they're tapping that interface. Sotra Patera, a feature imaged in 2004, looks volcanic. It's a 1,000-foot deep pit surrounded by flows that extend 15 miles. The spectra show different ice compositions than the surrounding terrain. But without catching an eruption in progress, the case stays circumstantial. The hydrogen anomaly comes from Cassini's ion and neutral mass spectrometer. It measured hydrogen near the surface at levels 40% lower than models predicted. Something is consuming it. Chemical reactions on the surface could do that, or something metabolic. Acetylene depletion follows the same pattern. Sunlight breaks apart methane in the upper atmosphere, creating acetylene that should rain down and accumulate. But surface concentrations are lower than expected. If microbes are oxidizing hydrocarbons the way Earth life oxidizes sugars, acetylene would be the obvious fuel. Dragonfly launches in 2028, arrives in 2034. It's a rotorcraft, 10 feet across, powered by a radioisotope generator. The mission plan covers 108 miles over 2.7 years, hopping between sites to sample different geologies. The primary target is Selk Crater, a 56-mile-wide impact site where liquid water once pooled. Impacts melt the ice crust temporarily, creating warm water lakes that last thousands of years. Organics dissolved in that water, concentrated as it refroze. If prebiotic chemistry got a head start anywhere, it's in those frozen melt deposits. Dragonfly carries a drill to retrieve samples from 4 inches down. The dunes cover 20% of Titan's equatorial region, dark streaks hundreds of miles long. They're made of organic grains, not sand, probably solid tholins that settled from the atmosphere. The grains are tiny, around 200 microns, smaller than terrestrial sand but large enough to saltate in Titan's winds. Those winds blow west to east, but the dunes run east to west. The contradiction held for years until researchers modeled Titan's rare equinoctial storms. Methane downbursts during storms generate gusts strong enough to reverse the transport direction, building dunes that point upwind. Vinyl cyanide was detected in Titan's stratosphere in 2017 using ALMA in Chile. It's stable in liquid methane and forms membranes that self-assemble into hollow spheres. On Earth, phospholipids do that job, but phosphorus is scarce on Titan. Vinyl cyanide might be the substitute. Lab experiments show these membranes stay flexible at -290 degrees Fahrenheit, the temperature of Ligeia Mare. They're less selective than Earth cell walls, but selective enough to concentrate molecules inside. If metabolism exists in those lakes, it's probably encased in vinyl cyanide vesicles. The isotopic ratios tell a timeline. Nitrogen-15 is enriched compared to nitrogen-14, meaning Titan has lost a huge atmosphere over billions of years. Argon ratios suggest the original atmosphere was 5 to 10 times thicker. Solar wind and photochemical escape stripped it away. That raises a question: where did the methane come from? The current atmospheric methane would be destroyed by photolysis in 10 to 100 million years. Titan is 4.5 billion years old. Something is replenishing it, either outgassing from the interior, cryovolcanism, or clathrate reservoirs in the crust melting episodically. Clathrates are cages of water ice trapping methane molecules. They're stable under Titan's crust at certain pressures and temperatures. If the shell thickness changes due to tidal heating or orbital shifts, clathrates could destabilize and release methane in bursts. That would explain why the methane hasn't run out. Cassini's final dive in 2017 sent back data until it burned in Saturn's atmosphere. The last measurements sampled the gap between Saturn and its rings, but earlier passes skimmed within 600 miles of Titan's surface. Those close flybys mapped gravity variations precise enough to reveal the ocean's depth and the shell's rigidity. The funding problem is real. Dragonfly's cost is $3.35 billion over its lifetime. NASA's planetary science budget is about $3 billion per year total, split between every mission and proposal. Mars sample return alone is projected at $11 billion. Titan competes with Europa, Enceladus, Venus, and a dozen other targets. After Dragonfly, concepts exist for a submarine to explore Kraken Mare, a probe to penetrate the ice shell, even a network of seismometers to study the interior. But approval depends on what Dragonfly finds. One biosignature detection changes everything. 0 detections, and the next mission waits decades. The question isn't whether Titan has the ingredients for life. It does. It's whether those ingredients have organized into something that persists, replicates, and metabolizes. Chemistry that crosses the threshold into biology. That line is blurrier than we thought. Either answer reshapes everything. We've sent one lander to Titan's surface, flown one orbiter through its atmosphere for 13 years, and learned more about prebiotic chemistry than the previous century of Earth-based research. The images are real, the lakes are there. The chemistry is happening right now, 886 million miles away. Titan's story isn't unique. It's a reminder that the universe doesn't care about our definitions, and the places we least expect might hold the answers we need most. Thanks for watching.